Indian Institute of Technology Delhi, also called IIT Delhi, embodies the best of higher educational ecosystem in the country. IIT Delhi is a confluence of minds, aspirations, and innovations, and is leading the way for technological advancements in the country. IIT Delhi is a 320-acre residential and fully networked campus. Recognized globally as a top-ranked institute, IIT Delhi's success can be attributed to its brilliant students, faculty scientists, R&D programs, and industry collaborations.
Originally, when IITs were established, these were mainly like undergraduate institutions. Same is true with IIT Delhi. We took pride in the quality of undergrads that we produce, but over a period of time, the character of these institutions got changed. Now we are recognized for our research contributions. We are recognized for contributions to the society in terms of the technology development. And IIT Delhi, for example, takes pride in being a top-ranked institution in the country.
Teaching excellence at IIT Delhi is inspirational for the young minds. And the academic attainments of the faculty are evidenced by their numerous awards and accolades. The admission to various academic programs at IIT Delhi is through highly competitive national level exams. IIT Delhi has numerous student exchange programs with several top-ranked global universities. In pursuit of academic excellence, IIT Delhi lays strong emphasis on cutting-edge and interdisciplinary research.
IIT is a great place to be in if you want to do research. We have a research environment which is buzzing with activity day in and day out. We have labs that work 24 hours, students working actively through the day and through the night in these labs. You would be surprised to know that we have more postgraduate students than undergraduate students here at IIT, that faculty spend almost 3/4 of their time doing research and supervising PhD students.
The faculty of IIT Delhi is involved in both open-ended research and goal-oriented focus research. We work closely with the industry and defense departments, space departments and other organizations. We bring problems from these organizations and jointly with our students we try to solve them, and also in some cases we develop prototypes, and when the complete technology is developed, we actually hand it over back to the organization for production.
When partners join hands, vision turns into reality. IIT Delhi has a number of national and international collaborations with industry and research organizations. Towards institutionalizing technology commercialization, IIT Delhi pioneered the establishment of Foundation for Innovation and Technology Transfer as an industry interface body in 1992. In 1994, it adopted its intellectual property policy, the earliest by an academic institute in India. IIT Delhi has a strong IP and licensing portfolio. The institute recognized the importance of techno-entrepreneurship early on. The creation of a technology business incubation facility in 2000 gave a huge boost to the startup ecosystem on the campus. The bright students at IIT Delhi continue to leave strong footprints with their ideas and efforts. Be it academics, sports, or social service, IIT Delhi students take the center stage.
Here in IIT Delhi, everybody is working on projects which is just helping the society come forward. Somewhere here on a crutches, somebody there working on smart cane, it just tells you, it gives you, motivates you that even you have to do something big or small.
Here you not only get to study things, you understand things, but here you get to know many more things instead of just studies. Like you get a great experience with the industrial people also.
Success breeds success, and the institute lays claim to several magnificent accomplishments. The illustrious alumni significantly contribute to the global image of IIT Delhi. And many of the alumni occupy leadership positions in various walks of life. Expansion, excellence, and inclusion form the core of IIT Delhi's Vision 2025. It articulates impactful research, quality education, and innovation programs. The quest for excellence at IIT Delhi continues. Indian Institute of Technology Delhi, also called IIT Delhi, embodies the best of higher educational ecosystem in the country. IIT Delhi is a confluence of minds, aspirations, and innovations, and is leading the way for technological advancements in the country. IIT Delhi is a 320-acre residential and fully networked campus. Recognized globally as a top-ranked institute, IIT Delhi's success can be attributed to its brilliant students, faculty scientists, R&D programs, and industry collaborations.
Originally, when IITs were established, these were mainly like undergraduate institutions. Same is true with IIT Delhi. We took pride in the quality of undergrads that we produce, but over a period of time, the character of these institutions got changed. Now we are recognized for our research contributions. We are recognized for contributions to the society in terms of the technology development. And IIT Delhi, for example, takes pride in being a top-ranked institution in the country.
The teaching excellence at IIT Delhi is inspirational for the young minds. And the academic attainments of the faculty are evidenced by their numerous awards and accolades. The admission to various academic programs at IIT Delhi is through highly competitive national level exams. IIT Delhi has numerous student exchange programs with several top-ranked global universities. In pursuit of academic excellence, IIT Delhi lays strong emphasis on cutting-edge and interdisciplinary research.
IIT is a great place to be in if you want to do research. We have a research environment which is buzzing with activity day in and day out. We have labs that work 24 hours, students working actively through the day and through the night in these labs. You would be surprised to know that we have more postgraduate students than undergraduate students here at IIT, that faculty spend almost 3/4 of their time doing research and supervising PhD students.
The faculty of IIT Delhi is involved in both open-ended research and goal-oriented focus research. We work closely with the industry and defense departments, space departments and other organizations. We bring problems from these organizations and jointly with our students we try to solve them, and also in some cases we develop prototypes, and when the complete technology is developed we actually hand it over back to the organization for production.
When partners join hands, vision turns into reality. IIT Delhi has a number of national and international collaborations with industry and research organizations. Towards institutionalizing technology commercialization, IIT Delhi pioneered the establishment of Foundation for Innovation and Technology Transfer as an industry interface body in 1992. In 1994, it adopted its intellectual property policy, the earliest by an academic institute in India. IIT Delhi has a strong IP and licensing portfolio. The institute recognized the importance of techno-entrepreneurship early on. The creation of a technology business incubation facility in 2000 gave a huge boost to the startup ecosystem on the campus. The bright students at IIT Delhi continue to leave strong footprints with their ideas and efforts. Be it academics, sports, or social service, IIT Delhi students take the center stage.
Here in IIT Delhi, everybody is working on projects which is just helping the society come forward. Somewhere here on a crutches, somebody there working on smart cane. It just tells you, it gives you, motivates you that even you have to do something big or small.
Here you not only get to study things, you understand things, but here you get to know many more things instead of just studies. Like you get a great experience with the industrial people also.
Success breeds success, and the institute lays claim to several magnificent accomplishments. The illustrious alumni significantly contribute to the global image of IIT Delhi. And many of the alumni occupy leadership positions in various walks of life. Expansion, excellence, and inclusion form the core of IIT Delhi's Vision 2025. It articulates impactful research, quality education, and innovation programs. The quest for excellence at IIT Delhi continues.
Welcome all. Good morning to our colleagues in the Western Hemisphere. Good afternoon and good evening to our colleagues in the Eastern Hemisphere. My name is Shantanu Roy. I'm a professor of chemical engineering at IIT Delhi, and I'm one of your co-chairs for the ISCRE26 and the APCRE09 conference. I'm joined here for the session with my co-chairs, Professor Vivek Buwa, Professor Vivek Ranade, whom you see on your screen, our head of department, Professor A.K. Saroha, and Director IIT Delhi, Professor V. Ramgopal Rao. Online, we have in this session Professor J.B. Joshi from ICT Mumbai, Professor M.M. Sharma from ICT Mumbai, and Professor Andreas Stephen Morgenstern from the Max Planck Institute. Professor Mike Dudkovich from Washington University and Professor Mike Harrell from the University of Houston will be joining us shortly, as would Professor Klavs Jensen from MIT. I welcome all of you, and indeed all our delegates who are joining us online on the conference platform, as well as other friends and colleagues joining us on YouTube, specifically for the inauguration session of ISCRE26. It is indeed a unique experience to be welcoming our colleagues from around the world on a single platform as part of the 26th International Symposium of Chemical Reaction Engineering and the 9th Asia Pacific Symposium on Chemical Reaction Engineering. The 26th edition of ISCRE was supposed to be held in New Delhi in December 2020. In fact, the original discussions around this started in the ISCRE meeting in Bangkok in 2014, followed by firming of plans in 2016 in Minneapolis, and then in 2018 in Florence. By 2019 end, we had started to roll out the arrangements in New Delhi. We were seeking abstracts and so on, and we are looking forward to welcoming everyone here. When COVID struck and the whole world turned topsy-turvy. By mid-2020, when the world was amidst multiple lockdowns with notable disruption of academic and research activity, the organizing committees, including the International Scientific Committee, were of the view that we may postpone the meeting to 2021, hoping for better times and keeping the option of an in-person event in New Delhi open. But as we all know, 2021 also had its own COVID waves. And by mid-year, when India too was hit by a massive second wave, it was clear that switching to an online option was a prudent way to go ahead. A further delay was not desirable. And as we realize now, with variants like the Omicron still circulating and impeding international travel, it was arguably the right decision. This meant a complete change of plans from an organizational perspective, as we had to cancel all our bookings and events we were planning for the in-person conference and move everything to an online platform. We, in fact, were looking forward to offering a unique cultural experience from India, but that is something which we had to postpone for a better time. Well, so here we are, and looking at the brighter side of things, we haven't had an overwhelming response to this conference. The online platform actually allows people from around the world to join in seamlessly. And it is clear that universities and companies globally have had a clear rebound in resumption of academic and research activities. We have a range of topics being covered and an impressive line of plenary and keynote speakers. We have also undertaken a few new sessions, as my colleagues will introduce, in order to tap into the flexibility that the online format provides in assembling the top experts around the world. We would have loved to welcome you, all of you in New Delhi, and in particular IIT Delhi, in person. Our invitation still stands, but for now, let us do the next best thing. Let us enjoy a virtual conference. I'm sure you would have enjoyed the virtual entry to the conference as you logged into the virtual platform. And now, to take you further through this program for the day, may I hand over to my colleague, Professor Vivek V, my co-chair for the conference. Vivek, over to you.
So thank you, Professor Roy. Since all of us are participating in this conference through this virtual platform which you have just entered, it is important that we have a closer look at the platform and some of the important features. So once you enter, you will end up in the lobby, and then you have this help desk where you can seek the chat support. So you have already passed these steps, so therefore I'm not explaining them here. So once you come in, you are here in the lobby, and the names are self-explanatory. You are currently in the plenary room where the plenary session is happening. The oral tracks, there are 4 oral tracks which will happen in oral sessions. You can visit the sponsors at the exhibitor. Some of their resource materials is also kept in the information center. All other resource material, including the agenda, the material by the sponsors, are kept in the information center. For the oral tracks, starting from tomorrow, you can go to these oral sessions, and you will see 4 parallel tracks there. Now, within these oral tracks that you have, these will run in the webinar mode. So this is the view that you are currently seeing. And when you want to attend the oral sessions tomorrow, you can enter one of these oral rooms. And then in the oral rooms, all of you would be on the webinar platform. And a unique feature of this is that you can interact with the speakers live for the Q&A. So whenever you have questions, you can switch on your mic and camera and interact with the speakers live. For the posters, you can click the posters menu at the bottom bar that you see. And then you will see posters for 6th of December and 7th of December organized in a thematic way. Another important feature is that you can also interact with the poster presenters live. And for this purpose, we have identified 2 slots, 4:30 p.m. to 5:30 p.m. And again, on the same day from 10 p.m. to 11 p.m., all in Indian standard timings, where all the poster presenters will be available, and you can connect with them through live, where you can talk with them, and interact with them. And that's a unique feature. You also have the networking room in which you can chat with each other. You can also talk to each other via the video call. Next presentation, please. Now, it's my pleasure to also provide you a brief overview of the conference program. We have the International Scientific Committee and the National Organizing Committee, comprised of eminent members who are known for their contributions to the area of chemical reaction engineering. Many thanks to them, as they contributed immensely to the organization of ISCRE26 and APCRE9 in the challenging times arising out of COVID-19 pandemic. This involved planning of ISCRE26 and APCRE9 initially in the in-person mode, then making tough decisions of postponing them to December 2021, initially to have an in-person conference, and again because of the difficult times, finally we decided to go fully virtual. While all these arrangements were made, the venue was booked to host the conference in person mode, and it was a tough time to switch to a fully virtual mode. We thank the ISC, the NOC, and also the local organizing committee at IIT Delhi in helping us to arrive at the best possible decisions and for supporting us. And of course, this would not have been possible without a generous support from IIT Delhi. Also, the Department of Chemical Engineering, the Foundation for Innovation and Technology Transfer, known as FITT of IIT Delhi, and the tireless efforts of the young student volunteers. I now quickly present to you a brief overview of the conference. The first call was issued in December 2019, and we received an overwhelming response. We received about 610 abstracts. Because of the postponement, we issued the second call, and we received about 130 abstracts. Each of the abstract was evaluated by at least 2 or 3 reviewers drawn from the NOC and ISCE and worldwide subject experts. And finally, in the conference that is beginning today, we have 156 presentations, including the oral and plenary talks by the distinguished speakers. We also have 113 poster presentations scheduled on 6th and 7th of December. Now, if you look in totality, we have participation from about 23 countries, with about 56% contributions coming from Asia, 26% from Europe, and about 10% from North America. Now, with this, I stop here and invite the chairperson, Professor Vivek Ranade, to give his opening remarks. Thank you.
Thank you, Vivek. Great. It's my pleasure to welcome you again to this 26th edition of International Symposium of Chemical Reaction Engineering and 9th Asia Pacific Chemical Reaction Engineering meeting. I'm Vivek Ranade. Currently, I'm Bernal Chair of Process Engineering at University of Limerick in Ireland. I used to work at National Chemical Laboratory in Pune before I moved to Ireland. And on behalf of my colleagues in India, I had proposed to host this conference, ISCRE26 and APCRE9, in India at the ISCRE meeting held in Bangkok in 2014. And that has resulted in this meeting. I continued to chair this conference even after I moved to Ireland in 2016 with the generous support from my friends and colleagues in India. Thank you so much. You have already met my co-chairs, Shantanu, Professor Shantanu Roy and Professor Vivek Buwa. Both are from IIT Delhi. Both of them have really worked tirelessly to make this meeting happen. As you know, I was in Ireland for most of the time. So both of them are really architects of this meeting. And welcome. So I once again welcome you to these two meetings, joint meetings of ISCRE and APCRE. These ISCRE and APCRE meetings have a great tradition and continuity, as you see here just by those names. This is the 26th edition of ISCRE, started quite long back, and the 9th edition of APCRE, which happens every 3 years. ISCRE happen every 2 years, so you can imagine that it's more than 50 years of history. The previous ISCRE, the last ISCRE happened in Florence in 2018, and the previous APCRE happened in Shanghai. I was participating in both of those, and the chairs of those two meetings, Professor Enrico Tronconi and Professor Xingui Zhao, both of them are also participating in this meeting. I'm just telling you this that just to ensure, just to convey the great tradition and continuity which this ISCRE and APCRE meetings have. Right, so you will get to know the organizers of APCRE and ISCRE, next ISCRE and APCRE meetings on Wednesday evening. Okay. While I said that, it's great to have you here, but we really miss meeting you in person. As Shantanu and Vivek, both of them have mentioned that we were really hoping to meet you in person, especially at least after postponing our event by 1 year. But this is not so. So but anyway, we are meeting now with this good online platform. I think India is a fascinating country, and I would like to urge people who have not yet visited it, I think, to experience it at least once. And that was the reason for we wanted to really meet you in person. Not just because of this magnificent historical monuments, some of them I have captured on this slide, or the great culture of several centuries or millennia, but also for India now boasts some of the finest educational institutes, chemical engineering institutes, reaction engineering experts, and Indian and the chemical industry. Indian chemical industry has made significant progress, and it can now boast of some of the first in the world category of technologies, and also including some of the largest reactors in the world. I think you will get to hear some of these ideas as we progress in the meeting. The chemicals and petrochemical sector in India makes significant contributions in Indian economy. It is $178 billion today, and it is expected to grow to more than $300 billion in 2025, despite COVID. So that's a significant growth. It makes 7% contribution to GDP, more than 50% contribution to industrial production, and more than 15% total exports of manufacturing sector. It is expected to grow at least 1.5 to 1.7 times of GDP growth. So it means that it will have a double-digit growth. India is already a second largest producer in Asia in terms of volumes. All this projected growth, if you really want to realize and sustain, chemical reaction engineering is crucial, and that is why it was important to bring this ISCRE meetings to India. Of course, just getting a decision to host meeting in India was only a starting point. To really make this happen, I once again express my gratitude to IIT Delhi team, Vivek, Buwa and Shantanu Roy, plus the larger IIT Delhi team, student volunteers, local organizing committee, and so on. We were also ably supported by national organizing committee, where most of the representatives from many educational institutes as well as large industries were contributing as a members of national organizing committee. We were ably supported by international scientific committee, who helped us in reviewing abstracts and so on. ISCRE board, the board of ISCRE Incorporated, as well as the APCRE committee have supported us. And last but not least, I also want to acknowledge the industry sponsors, Reliance Industries, Thermax, Corning, and Honeywell UOP for their support. I think we are really thankful to all these supporters. The ISCRE26 and APCRE9 special issues are being brought out, as I think many of you are familiar with this and know about this, by AICHE Journal and Reaction Chemistry and Engineering. All this, we want to thank all these supporters of ISCRE26 and APCRE9. With the support of all of you, we have, I think, created an excellent program for next 3-4 days. I'm sure you will enjoy that. Today, as an inaugural day, we have 2 inaugural plenary talks, which will be followed by a special inaugural day session on CRE, Chemical Reaction Engineering, and ISCRE Symposia, Past, Present, and Future. And we have 4 distinguished speakers as a panel for that session. Next 3 days, Monday until Wednesday, we have 6 plenary talks, 19 keynote talks, and more than 100 oral presentations and poster presentations. These oral and poster presentations are broadly grouped into themes like fundamentals, catalysis and catalytic reactors, process intensification, sustainable clean and sustainable energy and environment, sustainable process development, reaction engineering for materials, advanced materials, as well as some miscellaneous topics like product engineering and food and nutrition. At the end of this conference, we have a special session on future of reaction engineering, industrial perspective. Right. So this, I'm sure you will enjoy this exciting and rich, full program of ISCRE26 and APCRE9. Please enjoy your conference, participate vigorously, and make this conference more effective and productive. With this brief welcome remarks, I would like to invite Professor Ramgopal Rao, Director, Indian Institute of Technology, Delhi, to formally open our meeting, ISCRE26 and APCRE9. Professor Ramgopal Rao.
Thank you very much, Professor Ranade. Good to see you after a long time. I am very happy to be with all of you for the inauguration of the 26th International Symposium on Chemical Reaction Engineering and the 9th Asia Pacific Chemical Reaction Engineering Symposium, which are being organized by, I understand, multiple academic institutions in India, including a major role played by IIT Delhi. I would also like to use this occasion to welcome you all to IIT Delhi for this virtual event. IIT Delhi, as all of you know, has one of the finest chemical engineering departments in India, with a large number of faculty members and with a very vibrant kind of an activity happening jointly with industries and various government agencies. I also understand that this event is being organized for the first time in India. Had it not been COVID, I am sure we would all have loved to invite you to our beautiful campus. But of course, the benefits of doing a conference online, it has its own benefits. And looking at the list of speakers and the high quality technical program you have been able to put together, I guess you have utilized the opportunity to the fullest extent. I am happy to see the conference cover all major topics in reaction engineering, such as fundamentals of chemical research engineering, catalysis and catalytic reactors, process intensification and novel reactors, advanced materials, and also the most important of all, the clean and sustainable energy environment. As you are all aware, all these areas are of immense interest to a developing country such as India and of course to the rest of the world. The clean and sustainable energy environment are of particularly immense interest to India and the world at this time. India, as you all know, has set for itself some very ambitious plans in sustainable development and clean energy, as revealed in the COP26 summit. These include 500 gigawatts of renewable energy target by 2030 and becoming fully carbon neutral in the next 50 years. India, despite being a fast-growing nation with an enormous energy appetite, believes that the end of century global warming goal of 2 degrees centigrade is not enough, and we must target 1.5 degrees centigrade to avoid climate disasters. As the second most vulnerable country to climate change, India is now leading the climate war with a clean molecule as ammunition, which is the green hydrogen. India presently imports over 160 billion worth of fossil fuel energy, and if we don't do something, it is likely to get doubled in the next 15 years. COP26 in Glasgow presented India with an opportunity to present its decarbonization strategy based on renewable energy, storage, and green hydrogen to the world, where chemical engineers, I'm sure, need to play a very important role. In fact, I also recently came to know that in India, of course, the manufacturing and innovation capabilities are very critical to achieve the green hydrogen industry targets. To address low supply of electrolyzers in the world, India is building capacities for the production of 20 gigawatts of long-lasting electrolyzers in the coming decade. And as a nascent field, R&D investments become critical to the success of the Indian electrolyzer industry, where the roles of venture capital, academia, industry partnerships, and international collaborations are the key. I'm very confident this conference will discuss many of these issues, not only related to sustainable energy and environment, but all other aspects related to chemical engineering. I'm confident the conference will be a highly enriching experience for all participants. My best wishes to all of you who are participating and also to all those who are hosting the conference. All the best.
Thank you, Professor Ramgopal Rao. I now invite Professor Saroha, who is currently heading the Department of Chemical Engineering at IIT Delhi, to give his remarks.
Thanks, Professor Vivek Buwa. Dear ISCRE26 and APCRE9 participants, I, on behalf of Chemical Engineering Department, IIT Delhi, cordially invite you to attend the 26th edition of International Symposium on Chemical Reaction Engineering and 9th edition of Asia Pacific Chemical Reaction Engineering, which is being organized in virtual mode from 5th to 8th December 2021. Indian Institute of Technology, Delhi, which is organizing the International Symposium in Chemical Reaction Engineering, was established in 1961 by an act of Indian Parliament and was designated as Institute of National Importance in 1963. Recently, in 2018, it was declared Institution of Eminence by the Government of India. The Chemical Engineering Department at IIT Delhi also started in 1961, and today it is regarded globally as a leading chemical engineering department due to its highly qualified faculty members working in diverse range of research areas, technically skilled staff members, and the highly motivated students. The department's long-term vision is to become a world leader in technology areas of energy, environmental protection, novel materials, and healthcare. The department has been prolific in these areas and has done noteworthy research on the topics of materials development for energy generation and storage, catalysis and multi-phase reactor engineering, process intensification in non-renewable and renewable energy sectors, modeling and simulation from molecular to process scales, and bioprocessing related to the pharmaceutical industry. We would like to build on our strengths and strive for national and international presence in these areas by continuing our research and technology development initiatives. The endeavor is to develop sustainable technological solutions to some of the major challenges facing the society, such as bridging the gap between energy demand and supply, healthcare, food, environment, and climate change. Presently, the department is working on some national mission projects such as coal to methanol. We expect that these endeavors will not only attract excellent faculty, but will also provide and create an enabling ecosystem for students to explore, innovate, and make a smooth transition into the professional arena. The department is building focused research programs networked with industry, institutions, universities, and government agencies. We are working to develop effective and affordable technologies, scripting joint IPR in partnership with industry or through consortia leading to spin-offs. The department strives to promote a technology temperament in society at large, especially to young minds through extensional activities via technology-enhanced video and web-based distance learning courses, creation of virtual laboratory and resource centers, and participating in policy making and public debates. In addition to this, Chemical Engineering Department at IIT Delhi is committed to provide the best education to the brightest young minds. The academic program is meticulously designed to offer a wide range of courses that span from fundamental sciences to complex mathematical relationships and engineering design aspects of chemical and biological process technology. The department has a strong core curriculum at both undergraduate and postgraduate level and is complemented by various electives in the emerging areas. The curriculum is reviewed at regular time intervals to keep it updated in the context of the evolving discipline. The department has state-of-the-art experimental and computational facilities. The students are rigorously trained so that they are well prepared to be leaders in whichever field they choose to pursue, may it be academia, industry, technology management, entrepreneurship, or working for a social cause. Another important undertaking by the department is to maintain a vibrant research profile that truly captures the need and changes of the modern society. We believe it is essential to perform fundamental research alongside applied studies that cater to the broader economic, societal, and environmental development and growth of the country. This is achieved by hiring the best faculty across the globe and laying emphasis on problem solving through interdisciplinary research that crosses barriers across chemistry, physics, biology, and material science. Friends, we are meeting via virtual mode due to the prevailing pandemic. I wish you to stay safe and healthy by following the COVID protocols. Finally, a hearty welcome to all of you and hope that you will have fruitful deliberations over the next 4 days and come out with solutions to the various problems facing the society. Thank you. Thank you very much.
Thank you, Professor Saroha. Now, moving on with this program, we have the first inaugural plenary lecture by Professor J.B. Joshi. And it's my pleasure to invite Professor Joshi. On behalf of the National Organizing Committee and the Local Organizing Committee, it's my pleasure to invite Professor J.B. Joshi, Emeritus Professor of Eminence at Institute of Chemical Technology, ICT, Mumbai, and the Emeritus Professor at Homi Bhabha National Institute, Mumbai, to deliver the first inaugural plenary lecture. Professor J.B. Joshi completed his bachelor's and master's studies in chemical engineering from ICT, Mumbai, formerly known as the UDCT, in 71 and 72. He completed his PhD by research from ICT, Mumbai in 1977. And since then, he pursued his entire academic and research career at the ICT, Mumbai in different capacities. He was the director of ICT Mumbai from 1999 to 2009 And after superannuating from ICT Mumbai in 2009, he worked at the Homi Bhabha National Institute in Mumbai as the DAE Homi Bhabha Distinguished Chair Professor from 2009 to 2014. During his distinguished and illustrious academic and research career at ICT Mumbai, as well as at the HBNI Mumbai, he supervised close to 107 PhD students, close to 30 postdocs, and published over 580 papers and 74 state-of-the-art reviews and monographs, leading to more than 23,000 citations and an H index of 75. He contributed immensely to the areas of computational fluid dynamics, design of multiphase reactor, absorption of NOx gases, renewable energy resources, and development of new designs for household cookers and stoves, on which he is working of late. Professor Joshi has inspired several generations of PhD students who are contributing immensely in academia, in industry, in India, as well as in different parts of the world. His research contributions are recognized by several honors and awards bestowed upon him. The notable ones include the Shanti Swarup Bhatnagar Prize in 1991, the Vasvik Award in 1992, Dr. Anji Reddy Innovator Award by the Institute of Chemical Engineers in 2005, and the J.C. Bose National Fellowship of the Department of Science and Technology, and many more. There's a big list, and I choose to stop here. He is a fellow of Indian Academy of Sciences, Indian National Science Academy, Indian National Academy of Engineering. He is also a fellow of the World Academy of Sciences and also the International Fellow of the U.S. National Academy of Engineering. For his services to the field of chemical engineering and nuclear sciences, the government of India honored him with the third highest civilian honor, the Padma Bhushan Award in 2014. I feel proud and privileged to invite Professor Joshi this inaugural plenary lecture. Professor Joshi, please.
Thank you, Professor Vivek. Distinguished invitees and participants from throughout the world, good evening to some good morning. First of all, I express my heartfelt gratitude and appreciation to the organizing committee because they have made both ISCRE as well as APCRE successful in spite of several challenges. I also thank them for giving me the opportunity for delivering this inaugural plenary lecture on intensification and scale-up of multiphase reactors, contactors. I had an opportunity of more than 100 cases to analyze, design, scale up, intensify, troubleshoot multi-phase systems, and all of them are in successful commercial operations. So out of these 100 cases, I wish to make a presentation of 5 or 6 cases. As we know, in 2019, the global chemical industry had a revenue of $3.9 trillion and employed over 7 million people, which indicates the scale and size of the manufacturing operations. And it is making substantial contribution to the GDP. But in the coming 30 years, this manufacturing capacity is going to double, and the technology roadmap developed by International Energy Agency as well as DECMA identifies key challenges facing the chemical industry. And the challenges are, at present, the capital cost per ton is very high, sometimes preventive, and that capital cost should come down by 30% and in some cases by a factor of 2. Similarly, the energy cost should also reduce by 30% to a factor of 2. And accordingly, the GHG gases should also reduce, and many companies in the world, they have pledged for next 15 years to approximately 35 years that zero carbon footprint. Now these are very, very big challenges. In order to solve these challenges, in order to capture these challenges, the organizing committee has selected very apt words that if we want to make improvements in the reactor design, reduce the energy, reduce the GHG, then the 3 keywords are insights, innovations, and intensification. I have built my lecture around these 3 keywords. We know that in the early human endeavors, converting natural resources into products was achieved empirically by trial and error procedure. Hence, the pace of progress was slow. Chemical factories producing commodity chemicals like sulfuric acid, ammonia were already in existence a century ago. Design and operation of such facilities were treated as trade-specific skills which were acquired by experience and not necessarily transferable. This empirical situation or uncertain situation was reduced considerably by introducing 2 concepts, unit operations and unit processes. In unit operations, many operations became mathematically descriptable and the procedures also became very generalized. So the procedures for design, for say example, distillation, absorption, extraction, chromatographic separation, they look very similar to each other. Basis is the same. And because of the mathematical description, the reliability in the design, confidence in the design improved. One point I want to emphasize at this stage that many multi-phase equipment are used commonly both for unit operations and unit processes. For instance, plate columns are used for distillation as well as absorption, and absorption with chemical reaction such as manufacture of nitric acid. Fixed beds are used for catalytic reactions. They are also used for ion exchange, adsorptive separations, chromatographic separations. Stirred tank reactors are used for a variety of unit operations and unit processes. Coming to the multi-phase systems, all the multi-phase reactors and contactors. In contactors, reaction does not occur, but multi-phase complex interactions are there. All these are complex, heterogeneous, turbulent, multi-scale, and many other complexities. Further, the multi-phase reactors have complexity of mass and heat transports accompanied by chemical reaction. In a purely empirical method, processes are developed in the laboratory and scaled up through a series of pilot plants. It's an empirical method. Because of the absence of insight, the development of commercial processes usually take 5 years or more. The reactors and separation equipment therefore are being over-designed, resulting into high capital and operating costs, long startup times, and are difficult to troubleshoot. Therefore, I am now going to take 4 or 5 examples out of my experience and try to make a presentation that how some of these uncertainties were eliminated. The first example I'm going to present, I have schematically written A going to B going to C. This is a real example, but I cannot reveal the chemicals, as all of you understand, because of the company knowledge. A represents the raw material, B represents all intermediate products, and C represents most of the impurities. And we don't want impurities, we want as far as possible A to B. When the problem was there, the purpose conversion or the reactor utilization was 70% and the selectivity was 95%. Now I'm going to use these 3 keywords: insights, innovations, and intensification, how this situation was improved. For all the reactions, all the intermediates, as well as for all the byproducts, the in detail reaction mechanism and kinetics was investigated. Typically, such reactions are carried out in classical bubble column reactor, where the bubbles are formed at the bottom, hydrogen is passed, and these bubbles, they rise and they come up to the top. Since hydrogen has limited solubility, during the residence time of bubbles from bottom to top, they do not completely react, and most of the unreacted comes to the gas phase. The unreacted gas is then recycled via a compressor, and for a typical case, the power was more than 150, 200 kilowatts. So 70% reactor utilization, 95% selectivity, and very high energy consumption. This was the starting point. As said already, that A going to B going to C, including intermediates and raw materials and the byproducts, the kinetics was established. This is a catalytic reaction, and in this particular case, the catalyst was suspended by a balance between turbulent dispersion and settling of particles. Whenever particles suspend by the mechanism of turbulent dispersion, the catalyst concentration is exponentially decaying from bottom to top, and in most of the region in upper half, there is a very lean catalyst, and that is the reason for reactor underutilization. When we wish to have uniform concentration, then we need to increase the superficial gas velocity. The suspension still is exponentially decaying, but the uniformity improves. We have measured, as I said, the kinetics. So far, very low superficial gas velocity, where mass transfer coefficient is less, the suspension of catalyst is very poor and reactor utilization is low. At this mass transfer coefficient, the kinetics was analyzed, multi-phase kinetics, and it was established that A going to B was completely mass transfer controlled, and B going to C was completely reaction controlled. So at high superficial velocity, we get better catalyst suspension, not very good, but we have dissolved oxygen and we get C, that is the byproducts. At low superficial velocity, we get A to B, but the catalyst suspension is improper and reactor is not utilized. So optimization of superficial gas velocity, that was not possible, and therefore by proper insight, an innovation was introduced. A parallel pipe is now connected, which is vertical to the column. In the bubble column, the bubbles are released at the top and only slurry flows in the pipe. So in the pipe, we have only solid liquid slurry, whereas in the bubble column, we have gas liquid solid dispersion. Since gas has negligible density, rho g h at such locations is much higher than such locations. Therefore, the flow starts in this direction, moves upwards and takes a U-turn and moves downwards in the downcomer. The principal point is there is an upward liquid velocity, and the upward liquid velocity now satisfies the force balance of all the catalyst particles, that is gravity minus buoyancy is equal to drag, and all the particles are individually supported by upflow of liquid. And this upflow of liquid could be adjusted by selecting the proper hold up in the riser, as well as the geometry in terms of diameters and height to diameter ratio, as well as the sparger design. After introducing this, one important observation, very, very important point I would like you to note is the catalyst suspension job has been taken away from gas and no effort is required for optimization of gas. The entire job has been taken by liquid and catalyst suspension is uniform throughout, and this recovered the reactor utilization to 100%, and industry people are more wise and they take it even upwards in terms of the capacity utilization. Now, since catalyst suspension is not the job of gas, the gas could be kept equivalent to the mass transfer controlled operation, the low gas velocity, and that reduced the power consumption of compressor by a factor of 3. So whatever challenges I said at the beginning in terms of capital cost, in terms of energy cost, as well as in terms of GHG gases, all that has been satisfied. For the design of classical bubble column reactor or external loop airlift reactor, which I showed in the previous 2 slides, the current procedures are empirical. And I have listed here 16 empirical correlations and about 5,000 experimental data points and drawn a parity plot. Here you can see that for any experimental gas holdup, all these 16 correlations predict the holdup or mass transfer coefficient by the difference is even by factor of 10, and therefore the empirical procedure is very unreliable and we cannot have a confidence. Here, therefore, we are using 8-step procedure, which I am going to explain in detail. Prior to that, we have used for 5,000 data points artificial intelligence, and both for mass transfer coefficient as well as hold up, you can see a parity plot based on artificial intelligence where the difference is not more than 20%. Let me come to the 8-step procedure. The first step, as has been said, is insight, developing the insight. The reaction mechanism, the kinetics, the rate controlling step, and it is likely that From point to point in the reactor, the rate controlling steps are different. There can be one or two or three together, and we should be able to carry out, calculate the overall rate of reaction in step 1. Steps 2, 3, and 4 together gives the understanding of fluid mechanics. Therefore, in small transparent equipment, we do flow visualization using particle image velocimetry, laser Doppler velocimetry, ultrasound anemometry, tomographic studies. This is measurement. Depending upon the multi-phase system under consideration, whether it is gas liquid, liquid liquid, solid liquid, gas liquid solid, we carry out as a third step computational fluid dynamics. Those who do CFD, they know that several assumptions are made in CFD simulations. Similarly, in measurements also, we need to make a lot of assumptions. And therefore, the fourth step is comparison between CFD predictions and experimental measurements so that we validate each other. For further improvements, use of sensors, where huge improvements are continuously happening, these are also to be used for understanding the fluid mechanics. So the steps 2, 3, and 4 together, they help us in understanding fluid mechanics in single or multi-phase reactors. And in 100 cases which I have faced, all of them were multi-phase. At the end of step 4, we declare that we have understood fluid mechanics, of course in inverted commas. Step 5 is very, very important, most important. That is developing relationship between fluid mechanics, which is understood, and the design objective. The design objective can be catalyst suspension, as I explained in the previous example, or bubble or drop size distribution, phase holdups, effective interfacial area, mass or heat transfer coefficient, or for estimating backmixing, it may be dispersion coefficient. And now using this insight, and particularly step 5, we can carry out the optimization. I personally consider implementation to be really useful, because after implementation, we can gather a lot of data, and when big data are accumulated, step 7 can be continuously repeated, and using artificial intelligence, we can optimize this further. My personal experience is using AI, we can make improvements from 5% to even 30% increase in profits. Let me take the example of catalytic hydrogenation as a second example. Here, the gas is sparged below the impeller, and gas is broken into bubbles and distributed throughout the vessel. Unreacted gas goes to the gas space. This unreacted gas cannot be let to the atmosphere, mainly because hydrogen is very expensive and explosive, and it cannot enter the gas liquid solid dispersion because it has to flow against the hydrostatic head. Now this problem is solved by the principle of gas induction. Here, the same impeller is surrounded by a stator. When impeller is not moving, then the liquid level inside is same as the liquid level outside. When impeller rotates, by Bernoulli's principle, the pressure goes down, the liquid level inside goes down, and finally touches the impeller. And when pressure goes further down and below the gas space, and when passage is provided, gas flows this way and self-induction occurs. Of course, now here we need the relationship between fluid mechanics and design objective is the impeller design that we select should create low pressure region as possible at as minimum energy as possible. Therefore, we screened large number of impellers and we could get couple of impellers where those could be implemented. However, this understanding of the relationship continued. If we see large number of gas inducing machines, that for classical flotation machine for 1 kilowatt per ton, 0.1 liter per second is sufficient. There have been improved designs, but gas inducing impeller becomes attractive only when the rate of gas induction is 50 liters per second or above. And by optimizing the impeller design, the computational fluid mechanics and developing relationship between the low pressure region and the impeller design, we could get not only 50 liters per second, but further optimization has given 100 liters per second or more. This rate of gas induction, as I told you, 50 to 100 liters per second, as the impeller is located at the top, we can get excellent rate of induction, basically because hydrostatic head to be overcome is less. If the impeller is kept at the bottom, the dispersion is throughout the vessel, but the rate of induction is low. And therefore, it is important that when such a situation is there, that is the impeller, inducing impeller is located at the top, the gas liquid dispersion is concentrated only in the top, and most of the bottom region is not in action. Therefore, we designed another impeller and optimized that impeller, the job of which was whatever induced by inducing impeller, distribute those bubbles throughout the vessel. That was the job. And that was again done by the understanding of fluid mechanics and dispersion. We know that the best dispersing impeller are not good suspension impellers. Since this is gas liquid solid reaction, we optimize the suspension impeller. So this 3 impeller system were specifically designed: suspension impeller, dispersion impeller, and gas induction impeller. Now these have been commercially implemented at more than 100. I'm conservatively telling you this number, in the range of 50 to 50,000 liters, and all of them are in successful commercial operation. The earlier, these hydrogenation reactions used to take anything between 24 hours to 48 hours. Now it is taking 3 to 4 hours. So that much energy required is reduced, and GHG gases are also reduced. I'm going to now describe an air oxidation example. Initially, I will explain a simple textbook case. Here a bubble column is designed for 200 tons per day, 99% conversion. Inlet outlet concentrations are given. KLA from empirical correlation has been calculated. Hold up also is calculated. And the liquid phase completely backmixed. Gas phase plug flow, the volume worked out to be 132. And power consumption was 51.7. We know that when the liquid phase is made plug flow, and in large columns, the gas phase also goes towards backmix behavior. Here we are providing sectionalizations, the sieve plates, and gas is accumulated below the plate, and there is a resistance between the two stages for gas, and therefore gas and liquid both become plug flow. as both of them become flow, the volume is of course reduced. When volume is reduced, height is reduced, hydrostatic pressure is reduced, and energy is also reduced. The second drawback of bubble column is it is giving very high pressure drop and high power consumption. Therefore, here we sparge the gas in between top and bottom so that now gas is introduced against the smaller height of liquid and the power consumption of gas. The beauty of this design is though gas is sparged at lower pressure, it passes through very high pressure region, and principle I have already told you, the pressure at such locations is low as compared to pressure that is definitely adjusted, and the downflow of liquid is more than the bubble rise velocity. Now these three reactors, usual bubble column, I have told you 132 meter cube and 51 kilowatts. Sectionalized bubble column, volume reduced by 30%, power consumption also reduced by 25% to 30%, and airlift reactor power consumption reduced to half. So whatever challenges are there in present chemical industry, I'm sure all of us are revisiting. But I wanted to explain this example, but the real examples which we have solved is acetaldehyde to acetic anhydride to acetic acid. The price of acetic anhydride is always practically 2 times the acetic acid, and making the intermediate product is always beneficial. When this problem had come to us, the selectivity was about 30%. And when the experiments were carried out in the laboratory, we could find out the time, the mass transfer coefficient, and backmixing in the liquid phase, and the heat transfer in such a way that this is the insight, so that we could get the high selectivity. So the important feature was, which was very, very difficult, that is for the optimization of B, the heat liberated by oxidation was to be removed. And at very low residence time, removing the heat became really, really challenging. And therefore we introduced 2 innovations which I'm unable to share, but the result was the 30% selectivity was taken to 66% selectivity by the proper insight and introducing those 2 innovations. There is a capital, and so in some cases huge capital cost. There are limitations on capital cost per ton product and operating cost also, and there are limitations, and these limitations demand that the rate of dissolution or mass transfer coefficient should be as high as possible. And in one particular case, we wanted 1 second inverse, very high mass transfer coefficient. So in the external loop airlift reactor, by introducing internals and by adjusting bubble size distribution and height to diameter ratio and riser to downcomer ratio, we have been able to get that mass transfer coefficient value of 1 second inverse. Now the next example is optimization of gas liquid reactor again. Now here A going to B gives desired product, it gives intermediate products, and it gives so many of benzyl alcohols. Now B is a generalized case of organic compounds to be oxidized, and A is oxygen. And for the case of toluene, I have written byproducts like benzyl alcohol, benzyl benzoate, etc. All these reactions, the intermediate, desired, and all the side byproducts, they were investigated in the laboratory, and the kinetics was established. In a bigger reactor, when safety simulation was carried out, it was found that byproducts are formed when the dissolved oxygen is low. So that was great insight, and over-oxidation occurred where oxidation levels are high and catalyst concentration is also high and temperature is also high. And this understanding helped us in optimizing the dissolved oxygen, the catalyst concentration, as well as temperature. And here I have shown the schematically how the mass transfer was improved. Only improvement of mass transfer was not enough. Uniformity of oxygen was very, very important. Let me take case of froth flotation. Here feed ore is crushed in the range of 20 to 100 microns. Those particles which are hydrophobic, they attach to the particles, bubbles, and they go up to the top and join the froth. Those which are hydrophilic, they go out as tailings. For bubble particle attachment, bubbles and particles need to come together, and this happens by turbulence. Any turbulence less than that will not attach the particles. But if the turbulence is more intense than what is required, the attached particles detach. As we know, the turbulence is highly heterogeneous in stirred tank reactor, and near the impeller, the intensity can be 10 times more than at the bottom, near the wall and near the top. And really useful turbulence we get in some portion of the tank, and therefore the effectiveness is low. We have investigated the use of fluidized bed. The solid particles, spherical particles are fluidized by liquid. One very important observation we saw by using particle image velocimetry, that turbulence is homogeneous throughout the equipment. At any point, the turbulence is homogeneous. However, it was not isotropic. For spherical particles, the vertical intensity by transverse intensity was 1.4. Therefore, we took ellipsoidal particles, and ellipsoid, as you know, has a property of lift, and in turbulent flow, turbulent lift, and therefore these particles enhance the transverse turbulence and gave the homogeneous turbulence as well as isotropic turbulence. And in such homogeneous and isotropic turbulence, we carried out the performance characteristics. The usual mechanical cell at 5 kilowatt gave 45%, whereas the new equipment gave 80%. In other words, if you want 65% recovery, we need one mechanical cell, and if you want 65% of remaining, one more cell, and typically we use 4 or 5 cells. And this new equipment can recover most of the desired material in one stage. There is one more advantage in fluidized bed. We now need not crush and grind up to 40 to 100 microns, because in a fluidized bed, even 1 mm particles can be suspended and the power consumption goes down. As we all know, 7% of the world's energy is spent in crushing and grinding. There are still 2 more problems to be solved for the fluidized bed column, and we are on the job. I'm now explaining a case of chromatographic separation where the stationary phase is 15 to 40 micron particles. These are very, very small particles, and Argon's equation predicts about 1 atmosphere pressure drop in half a meter column. So we cannot take very long column, and in 1 meter height, we need to accommodate about 500 to 1000 theoretical stages. And this demands that the liquid distribution should be so uniform that all the particles should experience exactly the same fluid mechanics. Here I have shown one possible distributor on the basis of fractal. The liquid enters at the center, splits into two, splits into two, splits into two, and finally splits. Of course, this is a schematic, this is not the real design because I cannot publish the real design. But if you take remotest point, at the end of each point, red point, there is an inlet hole. So when we introduce liquid, 1, 2, 3, 4, 5, 6, and the nearest point is also 1, 2, 3, 4, 5, 6. So both the points are equidistant from the inlet and liquid distribution happens very nice. There are another two innovations required, but I told you the basic principle of what was the inside and what are the couple of innovations were done and implemented. But such finalized chromatographic separators are in actual commercial practice. For estimation of mass transfer coefficient, we did not resort to empirical correlations and we did direct numerical simulations for single particle as well as multiple particle. For single particle, you can see that the predicted by direct numerical simulations are very close to experiments, whereas there is a random Marshall correlation, there is a lot of deviation. Since we did direct numerical simulation for single particles as well as multiple particles, we predicted drag coefficient versus Reynolds number in the range of 0.1 to 2 into 10 raised to 5, which included drag cases, which could be, the entire graph could be successfully predicted. For finer particles, suspension viscosity could be predicted. The Ergen equation pressure drop could be predicted. The velocity void edge relationship given by Richardson-Zaki correlation could be correlated. In our laboratory, there was a mass transfer data available for copper dissolution, and we simulated bubble column by DNA simulation, and there was an agreement between predicted and experimental mass transfer coefficient. I will explain now the manufacture of CNT, carbon nanotube. In our laboratory, we needed CNTs and we floated worldwide quotations, and the quotation was depending upon quality in the range of $5 per gram to $25 per gram. I'm saying $5 per gram and $25 per gram. Therefore, this was the experimental setup. This is a furnace, the fluidized bed of about 10 centimeter diameter, 60 centimeters height, and fluidized particles were carbon black. Ferrocene was embedded inside as a catalyst. Nitrogen or argon was fluidizing medium, and acetylene or methane were used as starting carbon sources. As you know, in such gas-solid reaction, there are so many steps. There are 9 steps, we need not repeat. But when we investigated this in detail, which we call InSight, it was found that below 800 degrees centigrade, it is completely reaction controlled, and the pyrolysis of carbon-bearing compound is the rate controlling step. Above 800 degrees centigrade, the internal diffusion is the rate controlling step. So at about 800 degrees centigrade, in this fluidized bed reactor of about 5-liter volume, in 3 hours we could get about 10 grams, and this was very low capacity. When we wanted to increase the temperature for increasing capacity, it was diffusion controlled, and 800, 900, there was no increase in the rate. Therefore, we thought to use nano catalyst where internal diffusion can be eliminated, and we could use 1200 degrees centigrade and continuously started manufacturing the carbon nanotubes. Most important I want to emphasize is the qualities measured by all sophisticated techniques of our carbon nanotubes. They match all the specifications which are available in the world including the best one. Here is the costing. We have started manufacturing at 16 kgs per day is a capital cost and operating cost, and here is a electricity cost, and our cost of production is $25 per kilogram. I was emphasizing $25 per gram. Now it is being scaled up to 1 ton per day, and cost of manufacture is supposed to be $20 a gram. Last one, I'm going to explain a combustion case, a social problem. Number of families using biomass cook stoves in India is 200 million, and they are being operated at 12%. Improved thermal efficiency is up to 40%. Then India will save about $12 billion. Please note that $12 billion is equivalent to total profits of specialty chemical industry. So this single problem is very, very important to solve. There is yet another two reasons. One reason is 25 to 30% of the India's energy is spent in household cooking and generates more than 1 billion tons of GHG gases. Therefore, this problem is very, very important. This is a typical situation where GHG gases are liberated and the efficiency is very low. For understanding the problem, I took 20 workshops of housewives and asked them what are the problems. Is money a problem or there are some limitations? So they really explained, and I could take that as a stepwise design procedure. This is a schematic diagram. For the want of time, I will not explain. But the insight was the oxygen concentration should be some critical minimum throughout the gas, throughout the stove. Wherever it is not there, the efficiency is poor. At all the gas velocities, we drew temperature and oxygen diagrams and optimized this. And now we are getting first of all blue flame like LPG flame, but still there are opportunities here. This efficiency is about 50%. We feel that we can take it to 60%. We have sold about 500,000 cook stoves of various efficiencies and various generations, but the requirement of the society is much larger. One very important point I want to emphasize here, that if you want to distribute or propagate the social related technology, then we need to collaborate with social scientists because they understand what is the social mindset as well as how to remove the mindset, how to correct the mindset. So we natural scientists need to collaborate them. Fortunately, we have been able to collaborate. Here, after installing cook stove, I have been visiting those places to understand the problem. In Himalayan homes, the houses are kept warm by, again, biomass-based cook stoves. And here you can see the drudgery of women and young children for collecting the biomass. Normally, the pollution as recommended by WHO is 2.5 particles per meter cube. But in Himalayan homes, it can be even $6,000, 6,000 particulate matter per meter cube. Now here we are collaborating with Marathi Vigyan Parishad, Institute of Chemical Technology, MIT of Boston, USA, and UPES University at Dehradun. You will see the cook stove which I showed you, biomass-based cook stove, is also in MIT Boston. They are also experimenting on this problem. Because these social problems, we have understood that they have much, much greater gravity than the systematic problems. I could explain another 30 examples, but conclusions will not change. I have presented personal reflections on several real cases of first is eye insight, and this can be chemical insight or physical insight. The innovation comes from relationship between fluid mechanics and design objective. The intensification can occur by optimization of relationships developed in step 2. Use of sophisticated sensors and developments in multi-phase CFD is very, very useful. I have been benefited immensely. I have written another I like insight, innovation, intensification, implementation. Anyway, any benefit is implemented, but my benefit is after implementation, we get lot of data. We call it big data, and using artificial intelligence, we can further optimize. And as I said earlier, we can improvise, we can optimize, we can increase the profits by 5 to 25%. Therefore, fourth I is also important. I strongly recommend those who are doing research in social areas, the collaboration with social scientists is important. I wish grand success to ISCRE26 and APCRE9. Thank you very much.
Thank you, Professor Joshi, very much. I appeal the audience. They can put their questions in the Q&A button. So if you look at the top bar, you will find a way to put your questions. You can also the viewers on YouTube, you can also post your questions. Professor Joshi, I would like to start with a question posed by Professor Ali Haider. How different solvents influence the hydrogenation reaction on the catalyst? I repeat, how different solvents influence the hydrogenation reaction on catalysts? And he has requested if you could elaborate on this.
Yeah. The solubility of hydrogen is different in different solvents, and this will give corresponding rate of reaction, but this is a smaller effect. If the hydrogen has less solubility in less hydrogen concentration atmosphere, the catalyst gets deactivated. Therefore, we need to select solvent with good solubility for preserving the activity of catalyst and of course for getting the desired rate of reaction.
Yeah, thank you. While there are other questions coming in, I myself have a question while the participants post their questions. I think often we are involved in doing fundamental research, looking at these processes, multi-phase flow processes at the scales of bubbles, particles, drops. We do DNS. We also do the simulations of laboratory scale reactors. But often the challenge is that how to connect with the real life problems, right? From your talk, I think you showed us several examples where you have been successfully able to connect the fundamental research finally to solve some of the practical problems. So would you like to give your insight as to what needs to be done to bridge this gap?
Right. The first thing is the kinetics doesn't change with scale. What changes with scale is only hydrodynamics. And therefore, we in our laboratory, for all types of multi-phase reactors, for possible scale-up, say for bubble column reactor, we choose 15 centimeter diameter reactor, and beyond which the hydrodynamics doesn't change. Mass transfer coefficient at same superficial gas velocity, liquid velocity is the same, hold-up is the same, everything is the same. Similarly, for stirred tanks, we take minimum 50 liter in the laboratory and try to understand the hydrodynamics. Similarly, for all the majority equipment like bubble columns and stirred tank reactors, we have selected a minimum size to be investigated in the laboratory, which can be scaled. Of course, the insight is very, very important before doing this. And then with the help of insight, physical means hydrodynamics or fluid mechanics, and kinetics chemistry, both these together with some experiments in minimum size equipment has been able to give confidence. And of course, after implementation, as I have told you, further improvement is definitely possible.
Yeah, thank you. We have one more question coming in from Akshay Singan, and he is asking you that in your experience, how industry perceives recommendations of proposed design modifications, specifically based on the economic analysis done by the academia or from the academia.
Now, first thing first, when you begin as a consultant, first 4 or 5 years is a growth period where you face a lot of challenges, nobody listens to you, you are not very much welcomed in the industry, etc., etc. But during those 5 years, if you have given one success, then people start believing you. And if you start giving continuous successes, then a situation comes where whatever you say from the mouth, everything is implemented. So developing an excellent relationship, personal relationship with industry and academia is very important. And as I shown in one slide, this cannot happen by sitting in the university. All of us need to spend a lot of time in the industry, work with industry people, including night shifts, develop friendships, try to understand problems, and most importantly, give all the credit of solutions to whosoever you meet in industry. This is very important. And then you will start making friendships, and you are actually later on, you start fearing that whatever you utter from the mouth is getting implemented. So you will have to be better careful. So that kind of relationship we need to develop. And that happens by a continuous progress in the relationship.
Yeah, thank you. The next question is from Professor Balasubramaniam, I assume from the University of Kansas in US. So he is asking, and I quote, "I'm curious to know how affordable the high efficiency chulhas are and how friendly they are to use."
The high efficiency costs about 500 rupees. Its efficiency is 50%. Is there any other question? 50% efficiency and 500 rupees per piece.
And the second half of the question is, how friendly are they to use?
Yeah. They are friendly. They are more friendly than classical cook stoves. There is a lot of heat and pollution experienced by the housewives. This gives a lot less pollution. We are also doing computational fluid dynamics of houses so that how pollutant distributes. It was very important. That is, money is not important to the village people. The pollution is important. So whenever we visited them, they gave the important input that whatever improvements you do, inventions you do, it should reduce the pollution. And therefore, the friendliness really comes from the reduction in pollution. I think that is more important to the users as well as for me. In my future program, I first of all need to take it to 60%, and then I will see whether further room is available. So these are very, very friendly from pollution point of view, as well as heat loss point of view.
Okay. So, there are some further questions on, there's a question that in the area of CFD, in particularly the simulations of multi-phase reactors, there's a question that, in your views, what are the challenges that we have today? The question is that, is the field matured enough to go, or according to you, what needs to be done further? And I think that's the last question.
Yeah. There are problems starting from describing interface forces. There are many problems. While using DNS, the computational size requirement is very, very high. But if you keep on practicing, you keep on getting ideas of solving a real problem. Even we have simulated large scale 80 meter cube reactor using using computational fluid dynamics. So the answer is the field is not completely developed. The lift, drag, and many other the solution procedures, everything is difficult right now. These are not, there is no systematic stepwise procedure. Start from 1 and go to step 7 by which you are going to get answer. But if you have simulated more than 100, 200 reactors yourself, then you can solve this problem by making some assumptions and develop some reliability in your own solution.
Yeah. So thank you very much, Professor Joshi. On behalf of the National Organizing Committee and the LOC and IIT Delhi, we thank you very much for such a wonderful lecture. And now I invite Professor Shantanu Roy to introduce Professor Klavs Jensen.
Thank you, Professor Vivek V. So it is my pleasure to introduce our second plenary speaker for the day, Professor Klavs Jensen. Can we have his camera activated? Yes. So Professor Klavs Jensen, good morning. Thanks for joining us. And it's my pleasure to introduce Professor Jensen. Professor Jensen is the Warren K. Lewis Professor in Chemical Engineering and Material Science at MIT. He served as the head of the MIT Chemical Engineering Department between 2007 and 2015. Going back, Professor Jensen received his MSc in Chemical Engineering from the Technical University of Denmark, what is known as DTU, and his PhD in Chemical Engineering from the University of Wisconsin-Madison in the United States. His research interests include on-demand multi-step synthesis, methods for automated synthesis, and machine learning techniques for chemical synthesis and interpreting large chemical data sets. Professor Jensen is a co-director of MIT's consortium, Machine Learning for Pharmaceutical Discovery and Synthesis, which aims to bring machine learning technology into pharmaceutical discovery and development. Catalysis, chemical kinetics, and transport phenomena are also topics of interest, along with development of methods for predicting performance of reactive chemical systems. Professor Jensen is a co-author of more than 460 refereed journal papers and 175 conference publications, as well as 8 edited volumes and 55 US patents. His work has been cited over 60,000 times, and Google Scholar reports his H index to be 128. He's a founding editor-in-chief for the Royal Society of Chemistry journal, Reaction Chemistry and Engineering. Indeed, he has kindly agreed to publish a special issue of our conference in the same journal. Professor Jensen is the recipient of several awards, too many to recount really, but the most significant ones being the Alan P. Colburn Award, the Charles C. M. Stein Award, the R. H. Wilhelm Award for Reaction Engineering, the W. H. Walker Award, and the Founders Award of the American Institute of Chemical Engineers. He also got the inaugural IUPAC Thales Nano Prize in Flow Chemistry in 2012 and the inaugural Corning International Prize for outstanding work in continuous flow reactors and chemistry in 2018. Professor Jensen is a member of the U.S. National Academy of Sciences, the U.S. National Academy of Engineering, as well as the American Academy of Arts and Science. He's a fellow of the American Association for the Advancement of Science and the American Institute of Chemical Engineers and the Royal Society of Chemistry. It's a pleasure, Professor Jensen, to welcome you to your plenary talk.
Thank you, Professor Roy.
So if you could just share your screen.
Does that look correct?
Yes, it's just coming on. Yes.
So thank you very much to the organizing committee for the opportunity to provide this lecture. So I'd like to talk, as the title indicates, really about development of chemical processes, and particular chemical processes used in fine chemistry and pharmaceutical engineering, where development times are important. So when you do chemical synthesis, which is really, as you know, the foundation of most products, including polymers and electronic and optical materials. This discovery and development process requires repeated design, make, test, analyze cycles. You take your data, you design a molecule, you make it, you characterize it, you analyze it until you have what you're looking for. And one of the things I'll show today is how information technology, in particular machine learning and automation, can help accelerate that cycle. The other thing is that because the small volume chemical industry really relies on new products all the time, the tradition has really been to use batch, which of course is contrary to conventional chemical engineering and reaction engineering, where we always think about flow or where we have continuous processes. And so there's recently been a development towards being able to use flow chemistry, which is what the chemists call continuous processing, in applications for small volume chemistry development. And that is really to offset the potential difficulties of heat transfer or mass transfer challenges and so on that exist in traditional batch chemistry, and also to allow implementation of novel photoelectrochemistry. And then further, what has enhanced this is our ability to build miniaturized systems, which really helps us get information about reactions, kinetics, and so on, without having lots of material produced. What's really driving this in terms of the economics is we make fewer blockbuster pharmaceuticals, but there's a greater and many more pharmaceutical ingredients needed to be made. And so there's also many competitive products. If you have development of new products and consumer goods and so on, you want to be out there first, and you want to get your material in quickly. So there's shorter development time. And of course, we want to have improved emphasis on safety and process and green processes and on cost. At the same time, we have now all these modern techniques of being able to integrate systems and use machine learning. And along with that, the manufacturing platforms that enables us to actually relatively inexpensively build small automated flow systems that we could use for optimization. And so there has been a drive from batch to continuous. And as you are well aware, that in batch, it's sort of a repeated manufacturing. You fill your batch, you react it, you do a workup step, you fill it again, do another reaction, and so on. It's separated by workup steps. So this is very slow, highly manually intensive, and it typically involves large E factors because you have to do lots of separations or workups, and then often because you use solvents as a way to dilute the reactions to avoid potential runaways. So, and of course, it's challenging to scale all the way from the flask up into big batch reactors because of the mixing characteristics. So in the continuous, if we can telescope reactions, so if you can tolerate going from one reaction to the next without purification, and I'll show some examples of the challenges of that, you can then telescope these reactions. You could then have workup, and then you can have additional reactions before you go to isolation of your product. So this type of operation requires less space because you get much improved heat transfer and mass transfer. You can actually intensify your process considerably, and you generate less waste. Because of the improved heat transfer, you can now run highly exothermic reactions safely, and you can actually therefore expand your reaction space and be able to make many different reactions. Of course, if you can run in steady state operations with feedback from measurements, you can begin to do process optimization. You can begin to optimize the process. You can also optimize your startup and transition strategies. And all of this really leads to a reduction of risk and an increased plant productivity. And continues, and as we know from our work in traditional chemical industries, that the understanding of how to build a continuous process gives you really tremendous process insights into kinetics and transport phenomena. And then furthermore, this continuous process then really enables us to get into some of the green chemistry advantages of reducing waste, designing less hazardous synthesis, maximizing atom economy, using safer solvents and catalysts, and so on. So it's not surprising that many of the pharmaceutical manufacturers have really considerable efforts now in including continuous manufacturing in their pharmaceutical production. And flow reactors really, which in the early 2000s sort of were little miniaturized systems that people were playing around with in the laboratory, really have developed into scalable technologies. So there are technologies in the laboratory, and there's technologies that will allow you to go from the laboratory all the way to production. In these two examples here on the right-hand side, I've elected here to show examples from Corning and Airfeld, but there are of course many other types of systems around. The key thing about these types of systems is that they maintain high heat transfer and good mass transfer and well-characterized mass transfer in such a way that you can actually do seamless scaling from the laboratory up into 10,000 metric tons of production at this point, for instance, in the Corning technology. So these technologies have been established, and I wanted to discuss as an example the idea of using modular plants to provide flexibility. Imagine you could actually build an independent unit that you could use to integrate pumps, reactors, separators, with the necessary control element to do continuous processing of pharmaceuticals on location or on demand. In order to actually get these chemistries to work and be intensified, we typically run them at much higher temperatures and pressures than you would in batch. This allows you to get the reactions to go fast, so you can get high productivity out of a small plant. And if you have such systems, you could think about using these for development to make small production volumes that you need for the initial test of your product. And then you could maybe scale by just simply copy them. You could imagine using these as actually a production platform for generics in healthcare units. And they could also be used, of course, to do orphan drugs, the ones that are in small volume or difficult to make with conventional plants. And maybe perhaps these also could be used to step in and fix supply chain challenges. So here's an example of such a system. The system is shown here on the right-hand side. In the top part, the sort of reaction engineering part of it has the synthesis modules here. These are reactors and separators. The chemicals are here, pumps, and then the process control, and then of course the process monitoring. The backside, which was built by my colleague Alan Myerson, has the purification part. And this system was demonstrated to be able to make 4 different pharmaceuticals in the required purity to give to a patient, so in U.S. pharmacopoeia standards. And so, and you can see this is really classical chemical engineering unit operations. We have reactors, we have separators, we have more reactors, different types of separators, different types of reactors, packed bed or flowway or just a tube, and again, different types of separators, and ultimately then the downstream upgrading, which in this case was done in batch. And by adding in different types of units, you can make different pharmaceuticals, ranging from diphenhydramine and Benadryl, flulidocaine and diazepam to fluoxetine, and also known as Prozac. And don't ask us why the government wanted us to make that, but you can see this actually became a fairly complicated process that involved all the process units in it. And we've since continued with Tim Jameson and Alan Meyerson to work on these technologies to improve them and to shrink them so that we could go from basically a system originally that was 1.5 cubic meters down to one that is now 0.75, and also be able to do different types of compounds and ultimately be able to show that we could do semi-pharmaceuticals and the required purity in 4 weeks. Now, what actually that enables us to shrink these systems was the ability to make small reactors with good heat and mass transfer and the types of pumps and separators we use. So the reactors themselves actually consist of PFA tubing, so perfluorinated material that is enclosed into an aluminum clamshell, so to control the heat transfer, and also so to protect the operator when you operate these systems at high temperatures and pressures. And then this clamshell is itself inside a temperature controlled environment, so that if the operator has to pull it out, even if it's hot, you could still be able to do that. Or you could cool it down quickly before you pull it out of its bay. These then connect in like books, like books on a bookshelf. And then the separators here are actually membrane type separators. They use the surface tension to do this separation of the aqueous and the oil in the system. And so these have been used to do a number of systems, including ciprofloxacin, a general purpose antibiotic. And under Roger's leadership, we ran a whole series of campaigns over months to demonstrate that these systems could be used to actually make different compounds. You see here, there's a list of the 7 compounds. And what I wanted to point out is that this idea of having disposable plastic tubing or perfluorinated tubing that we could it really helps you in order to go from one compound to the next. You can see the cleaning here was relatively small of everything else. And of course, this is required if you need to change from one product to the next. The units were run for 400 hours at scale, and they probably altogether with testing and so on, probably ran twice as much as that. And you can see here the amount of doses that we made in the different compounds. We were supposed to make 1,000 doses of each of these, which of course is very easy for atropine. There was only 0.5 milligram, much more difficult for ciprofloxacin. And so you can see that's why this is at 250 milligrams here, that it takes so much longer for the collection. And also the preparation here reflects really the complexity of the chemistry. This is what the synthesis unit looked like in operations. These are the purification units, which are now continuous, and also the Tapperton unit. Again, it was built by Alan Meyerson's lab. And as just as a typical chemistry lab, you can see that chemical process unit, all the people are doing is just watching their screens, watching their process run. So we had these continuous technologies that we could use to make chemicals. And so the question was, how do you actually accelerate the chemical development? The first step in doing that is, of course, understanding the chemistry and being able to plan the chemistry. So could one actually make a system where you could go up and say, make me ibuprofen or make me some other compound, and a system would actually make this? So there are really 2 components that you would need to do that. One is that you need to be able to plan the synthesis. The second is that you need to be able to execute the synthesis. So in terms of the planning the synthesis, you could, of course, go and find your favorite chemical collaborators, which is what we have done for years with Tim Jameson and my colleague Steve Bookwell. But you would also want to have a general system that you could do this and that could build up and provide, that could do this relatively quickly. And so you generate information from historical, we could take and generalize information from historical data. This would be from patents, publications, databases. Then once you actually have that information and you have actually developed the synthesis plan, can you then build an automatic flow chemistry system that automatically will configure itself and perform the necessary synthesis steps? So those are the two parts that we'd like to talk about. So Connor Coley, for his thesis, did a beautiful job on the retrosynthesis aspects of this and much else. And Dale Connor led the construction of the system. So Dale Thomas led the construction of the system. So in terms of the system synthesis planning goals, we wanted to leverage techniques from data science and machine learning to develop tools that could generalize the historical information. We wanted to be able to propose retrosynthetic routes to a target molecule from viable starting compounds. And we also wanted to make sure that this was done in a form that chemists could assess which of the most promising pathways. So in some ways, what we're doing is generalizing known chemistry. So we were not trying to tabulate known synthetic routes to compounds or search for the exact literature precedents. There are better ways to do that, and there are commercial databases that actually would allow you to do that in many cases. So in terms of retrosynthesis, let's say you wanted to make nevarapine. You would first try and think about, well, how can I get to that target molecule? What would be my first step? Working backwards. And so this arrow is in the retrosynthetic direction. Of course, in the synthesis direction, you would actually go from the red box to the black box. So you start with a compound, you propose a reaction to produce this compound like the one we just have here. You ask the question, is it feasible? Well, you can't really answer that question unless you know what the reaction conditions are. So you need to propose the reaction conditions. Once you have the reaction conditions, you can predict the reaction outcome. If it's not feasible, well, then you have to pick a different reaction. If it is feasible, you could ask, is it viable? If it isn't viable, then you have to go back and try alternative reactions. And so you very quickly build out this tree of possible pathways from your starting compounds. And you can see in this case here, these are cheap. And so you could start here and work your way back. Of course, you still have to make this. And so in this way, we can build up a network that describes how to go from viable compounds to our final compound, which is what we would need to actually build the system that can synthesize the final target molecule. And we will need a way to select the best possible pathway out of this. So this automated retrosynthesis really requires 4 steps. You have to essentially propose what reactants would give your product. Then you have to find out what are the conditions for that reaction. And then you can predict the reaction outcome. And ultimately, you can put all of this together and predict how to get from the starting compound, from your starting compounds that are viable to your final target. So in order to do the first step, that is to propose the reaction, we use templates, technique that goes back to E.J. Corey, and actually before. So traditionally use pattern matching to essentially have reaction rules, as in this case with this amide reaction. You could, of course, then find other molecules that would have the same pattern as these, and you could use those as a way to propose a reaction. There are also template-free techniques that can do this. One of the advantages of the templates is that you can actually represent stereochemistry. There's also template-free techniques that come from natural language processing techniques. They sort of treat the chemistry as a translation process that can be quite accurate, but is, of course, a black box. And then to get around the templates and actually have less of a black box, people are right now working on graph-based models to do this. The other thing that once we actually have our reaction is what about the conditions? And so you could take information in the databases and try to predict what would be the best prediction for a given reaction, like this one. And so Hongyu Gao, when he did this, decided to do this as sort of a sequential prediction technique. We first started predicting the catalyst, then the solvent, then the reagents, and then ultimately the temperature. because you have to make these many different predictions, the true context is in the top 10 recommendations 60% of the time. And you can see here in this particular case, this ends up being a palladium hydrogenation reaction over palladium carbon in ethanol. But in many cases, the predictions are actually better than one would think, because, for instance, the algorithm predicts that you should use ammonia and lithium at low temperatures to run this reaction. The database actually says that there's water in there, but that's because that's probably what was used as a quench. Obviously, you can't run a lithiation reaction with water present. And so one of the challenges that we have is that much of the data that is tabulated does not have time sequence information. That is, at what point did you actually add in the various reagents? Similarly, in this particular case, this is essentially the same catalyst. This is just a question of the starting points to make this catalyst. And then there is some equivalence here between the bases and the solvents. That means that you could probably run the reaction also in the suggested ones rather than the ones that was in the suggested ones, just as well as the ones that were in the literature. So one of the challenges we have with these is just the prediction is the quality of the data. So these techniques can only be as good as the quality of the data that we have access to. So then the next thing is that we actually wanted to predict the outcome. Conacoli wanted to predict the outcome of the reactions. And the challenge there, of course, is that nobody publishes failed reactions. So how do we actually get negative examples? And so this was done by augmenting the examples with false alternatives. And because we have these templates, we can, from each precursor set or reactant set, generate many different possible reactions. And if they have not been reported, we'll assume that it's because that they're negative. Of course, it can also be that nobody's tried it or that nobody's found a possible way to actually run that reaction. So, but that's how we generated the negative examples to enable then the prediction of forward reactions. This was done by using a graph convolutional network, and by including not only the reactants, but also the reagents in the system so that you get the effect of bases and so on in the system. And so this is represented as a graph, and the convolutional is because you sum effects from different atoms. And from that, we can then predict the bond changes. We can predict the bond order. And from that, we can actually then combinatorially enumerate all the possible candidate products. Some of these products will not satisfy valence rules, so they can be ruled out very quickly. And then what you could do is, now that you have all these products, you can compare them to the actually observed species. And so you can learn which candidates are the most likely. And now that you know that, you can then use that information to actually understand how the different atoms react with each other. And that has the advantage of giving you at least some insight that you could use to judge with your chemical intuition. And this system, when it was developed, worked as well as any chemists, sort of as well as we compared it to prediction from experimental chemists and came out just as well. So now we have all of that. We then need to do the tree planning, and there are different ways this could be done. You need some way to guide your way through the system. Obviously, with a simple system like nevarapine here, where there are a few steps, it's not so difficult. But if you have much larger depth, many more branches, how do you actually find your way through this maze of different trees? And so there are heuristic ways this could be done. You could learn about chemicals complexity. You could look about reaction complexity, and then we can train models essentially to rank templates relevant to our products. And this is a technique introduced by Sigler and Wagler, which we chose to use, just like we also chose to use, like them, the Monte Carlo tree search algorithm to perform the retrosynthesis. But you could also use things like reinforcement learning to do this. So altogether, that means we now had a way to take historical data and run it into an automated synthesis program. And this is actually available. You could log into askus.mit.edu and try it out if you're interested. So in this, then we have the target compound that for each candidate, will look up the various reaction feasibilities. It will validate each step, and you could then use this to plan synthesis. And when it was originally developed, this particular compound was just announced at an ACS meeting, and Connor tried this and demonstrated that within 15 seconds, he got a nice convergent path to this compound. So, and of course, the machine had never seen this compound, the software had never seen this compound before. So with that, we have a way in which we can plan synthesis. Then we needed to actually build the system and do the synthesis. And so that means we have to have a system that can reconfigure itself, that can execute itself, and then actually perform the synthesis. And so Justin Lumnes, along with other postdocs and students from Tim Jameson's group, worked with us to do the chemistry. Dale built the system, along with a number of other students that helped. And so when you look at this whole stream here, then the key part that we really need is some way of taking the synthesis information that we have from the planning to actually have a recipe to run on the system. And you can make the recipe, but because of the difficulties of extracting reaction conditions, and because many of the reactions in the past have been run in batch and we wanted to run them in flow, you really needed expert input to curate these suggestions. But I think that's perfectly fine. You really do want the human input to all of these processes. That's very important. And that also allows you then to judge different pathways. And by using this synthesis path software, you're sure that you have actually looked at many different pathways. So actually, when we want to build this system, one simple way to think about this is I'm just going to build a bank of reactors. And if I want to run 2 reactions in a separation step, well, maybe I want a CSTR, or maybe I want a pack bed. And I may want to have 2 reactors of different length. And I'm in a second bank like this. And then I want different types of separation equipment. Maybe it could be just a simple mixer settler, or I could have a membrane separation. And then along with that, I also want to be able to add material at any point during my reaction cycles. And so pretty soon you have lots of reactors, which is kind of redundant, right? Because you're only going to use 1. You're going to use 2 in each process that you want. So the rest is sort of redundant. Lots of separators, but most important of all, you have a plethora of pumps. And these are, of valves. And valves, of course, is what leaks and typically have maintenance issues. And so valve reliability meant that we were reluctant to go that way, although I would like to point out that it is possible to build such a system. There was a very nice paper from the SRI people that had that demonstrate this kind of a process, where you could see here that you had different reactor units, and depending on how you do the switching, you could have different pathways through the system to do the synthesis. We decided instead to have a robot build the system, just like a human would, because this would cut down on the redundancy and would give us greater flexibility and automation, as I will show later. The reactor units essentially have a microfluidic starting point here where the fluids come in. There's a mixer here, as is shown with glycerin and water, I think, just to show the. And then there's a reaction area that is, in this particular case, is a set of PFA tubing that you, again, easily can replace. Another example could be a pack bed, or it could be a separator that could be sitting here. So this would be then my process unit sitting here. That process unit has an outlet unit that's connected to the outlet. And then the inlets to the reactors come from here. And so you could see, you could have different units put up, and then this whole process manifold is connected back to reagent manifold by the robot, just like an old-fashioned telephone operator connecting the person bringing to the person receiving the call. And then you could have a selector valve here if you wanted to make actually different types of libraries, for instance, and I'll get back to this. And so this is an example of making lidocaine using this system. So this is sped up 30 times. This is the end piece. Here comes a liquid-liquid separator, a large reactor, a 3 milliliter reactor, and a small reactor for the first step, which is faster. And then it connects up the processes back to the pumps with the reagents and reactants. And when it's done that, it will seal everything pneumatically. And you will notice that it will also shrink in this direction because the fluid actually flows in the backbone here. And then at that point, it runs the process, which involves 2 reactors and a separator. And when it's all done, it then flushes it, and then takes it apart so that you can go back and do another synthesis. And of course, then this robot could build a synthesis with a different configuration. And depending on what you have in your library of reactors, you could put in different reactors and different separators. So this gives us the freedom that we wanted to be able to make things. And this was demonstrated with different types of examples. We wanted to show that we could do back-to-back synthesis of aspirin and signinosol. Lidocaine and diazepam share a common reagent, so we thought that would be interesting to reactant, and that would be interesting to combine those, show that we could set stereochemistry. And then, as I mentioned earlier, the ability to very quickly with a selector valve dial in different compounds enabled us to then be able to do library synthesis, as in these ACE inhibitors, so basically blood pressure medications, or in these pain killer compounds, as another example. You notice here that the temperatures go up to 140 degrees C and 250 psi, or 17 atmosphere, which is what we did in order to accelerate the chemistry. So we wanted to work at high temperatures and high pressures to make sure everything stays liquid, of course. So the challenge was that this robot, when you don't speed it up, you can see how slow it is. And part of it is that it's a 6-axis robot, and you want to make sure that you have to compute the path that it has to take in order to place this reactor with micron accuracy in the process tower. So it would be nice if there was some way of doing this much faster. And also, we decided that we needed to reduce the dead time in all the flow volumes in the system. And so Annie Ruth Nambia worked on this along with Travis Hart and Tim Kulesa to make the system more faster, more repeatable, by essentially making a simpler robot that just does XYZ and rotate. So it can rotate, so it can pick up behind it, and then it can do XYZ to place all of this. The key invention that he came up with was how to include analytics. So we now have an analytics capability. So at any point in the synthesis, you could put in an analytical instrument. So in this particular case, this synthesis is what's like before. Was you remember we had a reactor, now we have an FTIR. You can monitor what happens in the first step. Then in the second reactor, in this case, there is an HPLC online, HPLC mass spec online, that you can monitor what happens in the final product. And of course, any other sort of inline possible technique could be put in through these modules. And you can actually see the HPLC and the FTIR is sort of behind here. The other thing you wanted to be able to do with this system was to optimize. And of course, you can easily optimize temperature, flow rate, and concentration. But for many of these kinds of synthesis, it's also of interest to be able to optimize the choice of solvent, the choice of catalyst, what reactor you use, what are your separation variables, and so on. And so I wanted first to demonstrate that the system now works faster. This is actually now real time. You can see the robot is going to change from a 1 mil reactor to a 3 mil reactor. The automated nature of this system, I think this is really was an important thing for us, and I think is what's driving automation is, of course, you don't actually have to be here to run these reactions. And so that frees Annie and everybody else up to think about the next set of experiments, why the system is actually performing, say, an optimization run where it makes multiple runs. So you can see now it picks up the 3 milliliter reactor, swings it around, and then we'll bring it over and position it in the process tower, and so that it gets. And you notice all the circuitry on the back of the module. Each of these units have their own control units embedded on them, so that they can be run independently and easily changed. So we are now at the point that we can talk about doing multi-step flow synthesis based on some of these predictions of the synthesis planning. So ideally, what we'd like to do is to telescope these and not have to do separation in between. But the challenge of doing this, of course, is you need chemical compatibility, right? If you have an extensive reaction B that improves reaction 1, but it interferes with reaction 2, telescoping is probably not going to work for you. And there are also situations where you have to do solvent switch because you need a different solvent to do the second reaction. There's also the issue that if you specify, and this is true for all these flow systems, as you know, if you specify the flow rate here, well, you also then, and you specify the flow rate of your incoming stream, you specify the reaction, the flow rate in this, the residence time in this system, unless you change the reaction volume. So the only way that you can actually independently now manipulate the reactor volume here, so residence time here, is to change the volume. So all of this means that, you know, the global optimal conditions are not necessarily the combination of the individual subsystems. Right. So first, to demonstrate this, Annie, along with Chris Breen from Tim Gamison's group, used the Sonitic synthesis as a tool. This particular synthesis got several suggestions of ways this could be done from the synthesis planning, and particularly the two first ones. The first one was you could start with an SNR reaction. You could then do a nitro reduction to make the amine, and then you could do the final amide coupling. Alternatively, you could actually buy the amine and make the amide coupling first, then do the SNR reaction to form the final compound. This showed up to not be particularly chemically feasible. This was a much better route. It was also ranked 1. And so this is the route that they chose. And it was nice that it sort of reflected the chemical understanding, and it also shows the importance of having the human in the link. So as a process optimization strategy, then the idea would be that we start off by reacting the nitropyridine here with the morpholine, form the nitro intermediate, which we then will hydrogenate to make, and then we'd use a gas liquid separator to essentially take away the hydrogen before we proceed. Then with the amine that's formed, we then do an amide coupling to make our final compound. So this sounds like a really great telescope process. The only problem was that when Annie started running this, we discovered that the palladium catalyst essentially degraded over very rapid time constants, or less than an hour, you would lose significant activity out of the palladium catalyst. And many different palladium catalysts was tried. Ultimately, the problem was traced back to a deactivation from a byproduct in the first step. And so in this particular case, you can't really telescope the system. What you have to do is you have to do an offline purification of the nitro intermediate. And if you do an offline purification of the nitro intermediate, the palladium reduction step is completely, the catalyst is stable over many hours, and you can run this for a long time. So this was done as a single step optimization, which I won't cover here. And then the rest of it was actually combined as one process in a multi-step process. So then this would be then this reaction that we would run. You start with the nitro intermediate and then go through the reduction to do the coupling. And in doing this, of course, you mix here your amine with the carboxylic acid, and you also have an activator, either HATU or EDC. And when you do that, you certainly get the product. You can also see here that there's activated intermediate of the carboxylic acid, which is an important reactant in the sextant, and also the amine here. You can see there's a small amount of the nitro that was unconverted here in this particular example. But the worst part is that there's this impurity, this guanidine side product. And that's actually comes from the promoter interacting with the amine. So our desired reaction is that the carboxylic acid will react with the promoter to form this activated ester, which then will react with the amine to form our final product. But the promoter also will react directly with the amine to make the guanidine side product. So in order to have the side product formation, the clear message would be simply to first react the promoter with the carboxylic acid and essentially use all the promoter before it sees the amine. And so that's essentially what Annie did. And so you now have essentially a convergent process. On one side here, you run the activation of the carboxylic acid. You then mix that with the amine here to form your final product. So now we have a complete synthesis that we like to optimize. And here we optimize the nitro to acid equivalents in this particular step. One could also work on, for instance, try different hydrogen pressures and so on. But in this case, we fixed the hydrogen pressure at the maximum, thinking that we would want to have this reaction run as fast as possible. In this particular reaction, for the amide coupling, there's a question about whether you have enough residence time. And so it would be useful to actually use the robot's ability to configure volumes in mid-run, as remember I showed you, as a way of changing different residence times volumes in the system. So by changing to different volumes, we can change the residence time. The residence time is a continuous variable because we can change the flow rate continuously. But of course, you can do this in discrete intervals if you change the volume. And then, of course, we can change the temperature. Then, in addition to that, we wanted to try different promoters. And so we now have a system that has multiple continuous variable. It has one discrete variable and two objective functions. And so to do this optimization, Annie chose to use a Bayesian optimization developed really for machine learning applications, but it actually works quite well for these kinds of problems. It can handle both the continuous and discrete variables and multiple objectives. So this is actually what the system looks like. So there's one process tower where you do the activation of the carboxylic acid. That output is then sent in to react with the product from the reduction step. So here's the packed bed reactor. Here is the separator that takes out the hydrogen. There's an infrared spectrometer that measures the extent of the reaction in the reduction step. And then here, we have the amide coupling, and then we measure here finally the quality of the product form. And also we monitor the activation of the carboxylic acid with infrared spectroscopy. And just as to remind you, we then use the robot as a way of quickly changing the units around. And so with that, here are sort of the results of some of these optimizations. So we really have two things of interest to us. We are interested in high yield because that impacts the purification later on. And we're interested in productivity, and the size of the dots represents the productivity. So you like a big dot, and you want it as red as possible. And so you could see here is the outcome that then shows us we should run at high temperatures. We can actually do this at relatively short times. And with the increased amine equivalent here, we get really good productivity out of the system. So these have been examples that I wanted to show about how we can use continuous flow techniques at different scales to intensify traditional pharmaceutical batch and fine chemical batch manufacturing. We've used here machine learning to really do the planning of the synthesis. You could also use the machine learning to predict properties that you need. And ultimately, you can combine these things to predict new molecules that haven't been synthesized before. And so you could use the technique to, first of all, predict new molecules, their particular properties, then whether or not they're synthesizable, and then actually use these techniques to make them. But that's another story. But this will really, I think, accelerate how we think about developing chemical processes. And the computer-aided techniques that I've shown in terms of retrosynthesis also can be extended to understand things like impurity and selection of solvents and using green optimizations and so on. And of course, if you have these automated systems, you can do mini runs and you can actually vary things. You can do transients, experiments that will help you essentially plan kinetics and optimization. And once you have the kinetics and once you understand the transport phenomena in the system, scaling using standard chemical reaction engineering techniques will then really very feasible. And then I think these units that I've shown you, they integrate flow control, reactors, workup units with process analytical techniques and robotics, really allows you to do multi-step synthesis, and it can be reconfigured. So you can imagine that you could use these in development of small-scale production, or even perhaps in distributed manufacturing. Now, there are a lot of people that contributed to this work. We obviously could have done nothing in machine learning had it not been for our patient collaborators in computer science, Regina Basile and Tommy Yakala. All these chemistry examples I showed you today was really done in collaboration with Tim Jamison's group. And Bill Green provided a lot of insight into both the property predictions and so on for the machine learning part, as well as the retrosynthesis. And then, of course, there was a large number of graduate students and postdocs working on these projects. And I've sort of tried to highlight the key individuals as we went through. I've talked about Connor's retrosynthesis, Dale's robotic system, and Annie is sort of the version 2. But a lot of other people contributed to those over the past several years. Luke Rogers here was the person that sort of led a very large team of researchers in demonstrating that we in fact could do this 7 pharmaceutical compounds over a month campaign. And then of course, we'd like to thank our sponsors, Novartis, who really got us well trained in pharmaceutical processing and kind of continuous processing for pharmaceuticals. Dauber, who sponsors most of this work I talked about, and then the Machine Learning for Pharmaceutical Discovery and Synthesis Consortium, which continues to support our efforts to bring machine learning into pharmaceutical processing and chemistry processing. And with that, I would be very happy to answer any questions you might have, and would again like to thank you for the opportunity to present.
It was indeed, thank you, Professor Jensen. It was indeed a fascinating lecture. And some questions are coming up on the chat. So I will start with a question and comment from Professor Balasubramaniam of the University of Kansas. He says, thank you for a fascinating presentation. I have 2 questions, so I'll ask the first one first. Does your automated analytics provide product quality analysis, metal, solvent, etc., to meet FDA specifications?
To meet every
FDA, Food and Drug Administration specifications.
FDA, so we could use FTIR, for instance, as a monitoring tool, but of course that's not enough to get accuracy. The standard tool for that is the HPLC. But of course, if you also want to do things like metals and so on, you have to do those analytic techniques separately.
Okay. And the second question from Professor Bala is, can you please comment on the ease or difficulty for FDA violation protocols for this new paradigm of pharma manufacturing?
So FDA has been very much a proponent of continuous manufacturing and also the monitoring of the processes. So I think that is all things that they would like to see happening. The thing to remember about the FDA is that they don't approve the equipment, they improve the process for making a particular pharmaceutical. And so one of the challenging things that exist at the moment for these types of systems is that, of course, if you want to build a system that can make multiple pharmaceuticals, you would like to actually have it approved in general to make pharmaceuticals rather than having to have it approved for each compound that you have to make. But right now the rules are that the process is what's approved, right? So you have to, for each pharmaceutical you make, you have to get the FDA approval for that. And there are people, Luke Rogers and others I know are now involved in a commercial enterprise. They're actually trying to go through that pathway.
Thank you. So there's a question from Mr. Soumendra Banerjee, who's from Honeywell. He says, what is the maximum temperature and pressure we can go to? I believe he's referring to the robotics enabled synthesis that he was showing. So his question is, what is the maximum temperature and pressure we can go to?
So, so that depends on what you use as your materials for construction. So the units that we built, they use as PFA tubing. We limited to 250 degrees and C and 17 atmospheres. You could probably go a little higher in pressure and a little higher in temperature, but we thought that those were the safe limits. Now, if you were to use stainless steel manufacturing, you could build units that could go much higher in pressure.
Okay, right. So there's one question from Rajesh Mahendale. He says, will there not be an increase in the E factor if the entire assembly had to be flushed after a particular synthesis is completed, as compared to flushing a single reactor vessel?
That is true, but you're flowing very little through this, right? You could just add up you should really think about the reactor volumes and the surfaces that you have to flush. And so if you're flowing material through here, there's actually a relatively small volume that you're throwing through relative to, a large volume. And so I would think it would be a lot less than dealing with a batch process. And of course, you should compare it to a batch process where you have done all the steps.
Right. So, Professor Jensen, thank you very much. I think we're just on time for moving on to the next part of the proceedings of this inaugural session. So thank you again very much for a very, very fascinating presentation, and really appreciate the organizing committee, really appreciates you taking your time, that too very early in the morning in Boston. Thank you very much.
Thank you. Thank you for the opportunity.
Yeah, thank you.
Real pleasure. And so for the next and last part of today's inaugural session proceedings, may I invite now again Professor Vivek Ranade for proceeding with the special session on the perspectives on ISCRE, the past and how we are moving into the future, both ISCRE and reaction engineering. So can we have Professor Ranade back on the screen, and along with Professor Mike Yudukovic, Professor Sharma, Professor Andreas Seidel Morgenstern, and Professor Mike Harrod.
Hi, welcome. Welcome, Mike. Okay, great. Welcome, Professor Sharma. Well, I think let's wait for Mike Harold to join, and then probably we can begin. Just wait for a minute or so. Oh, yes. Hi. No, I said we'll wait for a minute till Mike joins. Okay, he's here. Yeah.
Oh, my mic.
Mike Harold. Yeah, Mike Harold. Sorry. Sorry for the confusion. Yeah.
Again, like yesterday.
It's okay. He said it's fine.
Is it okay now?
Yes, it is fine.
Yes. Okay.
Okay, great. So I think both the second mic has also joined. So let me welcome all my four speakers for this session, and of course all the audience for this session on CRE and the ISCRE Symposia, past, present, and future. I think before we begin our this special session on CRE and ISCRE, past, present, and future, I would like to pay respects to notable reaction engineers whom we lost in recent times. These include Professor Levensfield, Professor Fogler, Dr. B.D. Kulkarni from NCL, Professor Arvind Verma, and Professor P. Ramchandran. I think that is an irreparable loss to CRE and to CRE community as a whole. I'm sure that their work will continue to motivate many generations of reaction engineers in present and in future. Coming back to this special session, this ISCRE26 and APCRE9 has an overarching theme of insights, innovations, and intensifications via CRE. This is indeed crucial for the global quest and goals for responsible resource usage and the zero emission, net zero emission, decarbonization, and so on. The success of net zero goals rests on minimizing byproduct formation as well as minimizing the carbon footprint of multi-phase reactors and processes, which are really the core of chemicals and materials manufacturing. And of course, CRE plays a very important and crucial role in these achieving these goals. Today, we are almost at the end of 2021. I believe that it is a good time to reflect on various Vision 2020 documents which many institutes worldwide have prepared. I think AICHE had prepared, like Institute in TIFAC in India has prepared. So there were many Vision 2020 documents. I think it is good time to reflect on what fraction of that vision has been realized. Whether there is anything new which was not anticipated then has become important. I think it is an important juncture. Today, decarbonization, resource efficiency, and enhancing productivity have really become pressing issues. And multi-scale approach ranging from ab initio calculations to designing a single catalyst site to multi-scale models for complex large reactor hydrodynamics. Several new tools are enhancing capacity of reaction engineers to gain new insights. The new digitalization has created a lot of buzz. So sensors, cheap sensors, real-time data analytics, machine learning, and cyber physical platforms. Professor Klavs Jensen has just shown us the example of that, has created a lot of buzz. And all of these may have unforeseen implications and potential for chemical reaction engineers. Of course, these are very, very many new developments, and it is impossible to include all of these in a single session. In today's session, what we have done is we have brought together four distinguished speakers for this session who will speak on CRE, ISCRE, and of course, past, present, and future. I think ISCRE provides an ideal platform to have such discussion since it brings together many generations of reaction engineers. I mean, today we have Professor Sharma here, Professor Joshi, myself, Vivek Buwa, and his students. So all five generations are going to present in this ISCRE. And not just this, I'm sure there are many such generations, a family of generations are speaking at this ISCRE. Like, for example, Mike Dudukovic, Shantanu Roy, Rajesh Upadhyay, and his students, and so on. So I think we have a good platform here which can really be used for brainstorming across multiple generations of reaction engineers and discuss the past, present, and future of chemical reaction engineering. Right. So today we have these four speakers, which you see here today: Professor Mike Dudukovic, Professor M.M. Sharma, Professor Andreas Sidel Morgeston, and Professor Mike Herold. Each of these four speakers will share their thoughts in about 10 to 12 minutes today. We will have these four talks one after the other, and we will have all the questions at the end, which can be either be addressed by the whole panel of four speakers. If you have any question for a specific speaker, please include that in your question, so that when I'm reading the question, I can address it to the appropriate person. Please use chat box for sending your questions. And with this very brief comments and introduction for the session, I think let us begin with our session. And I would like to invite Professor Mike Dudukovic as our first speaker. I'll briefly introduce him before handing over floor to him. Professor Milorad Dudukovic, or Mike Dudukovic for many of us, is the Laura and William Jens Emeritus Professor of Environmental Engineering at Washington University in St. Louis. He is well known in his research and contributions in advancing the frontiers of reaction engineering and effective use of reaction engineering methodology to variety of multiphase reactors, as well as for developing new environmentally benign processes. Unique features of his research involve use of radioisotopes to monitor and map various multiphase flows and to generate data, crucial data for validating advanced models and theories in this complex area of multiphase reactors. He has worked for decades on developing a systematic approach for multiphase, multi-scale problems in CRE. He established Chemical Reaction Engineering Laboratory, CREL, which many of us are familiar with at WashU, and has mentored generations of reaction engineers. He has over 350 publications, and he is quite active professionally. He has organized more than 50 sessions at AICHE annual meetings. He was also the president of ISCRE Engg before, as well as chairman of AICHE CRE division. He was also as a long stint as an associate editor of INDC Research. He has received many awards, including the AICHE R.H. William Award in Reaction Engineering, as well as I would like to mention the 2016 Amundsen Award for Excellence in CRE by ISCRE. Today, he will be speaking on reminiscing the ISCRE Symposia and evolution of CRE. Professor Dudukovic, it's your floor.
Thank you, Vivek. Thank you for inviting me. I enjoyed visiting India back, and I'm although via virtual form, and I also enjoy seeing many of my friends that I met in previous visits. And I want to congratulate you in these rather difficult times, pulling off such a well-organized meeting. Now, I'll have to be obviously very brief, and I just want to say that ISCRE played an important part in my academic life and research, because I always enjoyed and felt that reaction engineering is uniquely important to the chemical engineering profession. And not just from the process side, but also from the environmental side. And I always hope that we can establish a systematic approach how to do this. And so coming back just to say a few words about ISCRE. ISCRE started in the 50s, 60s between the European countries. The leaders was Raoul Westerterp, who had a distinguished career at Shell and then later at Twente University. And he and Kramers put up the first publications that provided the systematic approach to industrial scale reaction engineering. Then, since I joined Washington University, I always had a dream to making the multi-scale approach universal for reaction engineering problems. And we we managed to produce a large echelon of graduates with advanced degrees who utilize that. Many of them are from India, many are from China, but what was pleasing to me as I started going to fewer and fewer meetings with age that these graduates are present, a large percentage of the audience and participants at ISCRE meetings, even in the one that you have here. There are quite a few of them present, and many present their work, and also they participate in forming the agenda. Now, ISCRE, of course, later grew from a European meeting to a European North America conference that switched from continent, American continent to European and so on every 2 years. And then it grew beyond there, and now you have ISCRE offshoots both in Europe and the NASCRE and other names, and also, as you well know, in your part of the world, in the Asia-Pacific forum and things like that. My great, not great, but significant disappointment came in the late 90s, or even early 90s to late 90s, when ISCRE and reaction engineers didn't do enough politically to change the course of how will Asia industrialize, produce chemicals, produce fuels, produce everything. And I said at many meetings, even semi-jokingly only, that in the process, the countries like India, China, and others who certainly have a fantastic educational background, both the Western post-World War II or World War II technology, spruced it up with few computers and started running processes. Yes, am I supposed to answer questions now?
No, go ahead, please, Mike.
I think Professor Sharma was waving to me.
No, he is trying to adjust something on the computer. Go ahead.
Oh, okay. So anyway, that was a disappointment because by using the multi-scale approach, which we taught our students since 1974, when we formed the CREL lab, with the objective that has never changed, that the task of reaction engineers worldwide is to eventually provide energy and material needs for the world through clean processes, and that can only be done by analyzing and scaling up these processes through the proper application of the multi-scale approach. If you think about it, the basis for this are still just mass and energy balances applied to small scale units, whether or without physical boundaries in the process, tying them together with known equations of transport and flow whenever possible, and coming up what the effects will be. Now, a whole generation of computer models that were generated in the already in the 70s and so forth, do that. They do mass and energy balances. They add to it on occasion rules of thermodynamics. And then they play with departures of equilibrium like we played in the old separation units decades and decades ago to figure out what might happen. But the processes have no base in reality for that reason, because the dynamics, the kinetics, the transport was never properly taken into effect, and needless to mind, without dynamic systems, you cannot have proper control, you cannot institute what you need for better performance often, which is cyclic or dynamic operation. Now, in propagating through CREL, the education of training of students in multi-phase reaction systems through the multi-scale approach, advancing reaction engineering methodology via research, and constantly working with industry to transfer state-of-the-art reaction engineering to industry, that would be a reasonable road to success. Well, the variations of how things are done in funding over the world prevent that. We have risen from a single investigators, myself, Professor Ramachandran, and so on, forming small groups. We have risen from support of 3 companies when we started in '74. That's why Ramachandran also joined us later, and so on, to over 40 by the end of the 80s, beginning of 90s. And then the culture really changed. The leaders of technical companies are not anymore engineers, chemical engineers and so on, that then later took an MBA course. Throughout the Western world, they are now lawyers or business people who only see the bottom line. A vice president of, say, let's say, Eastman in the old days, or Conoco, can come to my office, look what we do in 2 words, which I explain now to you. He would say, well, are we part of that group in the old days? And we said, no. He would say how much we need to be part of the group. Nowadays, you need to write interdisciplinary proposals and so on, which is one of the largest waste of time, because 1 out of 25 get funded. That's the American syndrome here. When environmental engineering got very popular, they've had an official already web page that showed in the environmental engineering division of NSF, 1 out of 35 proposals the previous years got funded. I can hardly think of a bigger waste of time of our productive young faculty and things like that. So I think that was part of the reason, and we somehow have to have a political influence through ISCRE, mainly through the corporations, because universities have given up on this, at least in the States. Most universities in the Ivy Leagues and those that aspire to that status don't have engineering, accredited engineering. Why? Because it's much easier to teach computer programs that how to do the business calculation and extract money from something. So I have digressed, but really what I am trying to say that if we want the future for our discipline to be bright, we have to understand that we are finally on the right path, that more and more of us use the multi-scale approach in designing and interpreting results to reactors, that we appreciate the need for experimentation on all scales because of scale-up issues, because of understanding of what's going on, and we really need to enforce that somehow, that without that approval cannot be given for a new process. That just copying the old technology, because that will save money on the short run, will also cost more money on the long run, is should not be tolerated. Globalization has helped our cause a little, because when I was monitoring here in St. Louis area, how we responded to the first call for making your house clean in the 80s in environmental initiatives, and we had the 16 bad guys, chemicals that we should get rid of. Well, everything that we could improve by doing better housekeeping, which was abysmal in the 70s and 80s, was adopted. Everything that required minor changes was adopted and process refurbished. Anything that required anything more, the solution was sell the process to Asian country or somebody else, let them make it however they want, clean your hands from it, and be happy that you don't have a problem on your back. But how did that globally reduce the impact on the world? No way. So that can only be prevented by having really global regulations. So I would suggest that in the future, instead of these wonderful sessions that we have and always had on showing what's new, what we can do with the newest possible technology, we should really select some key problems today, problems that generate unbreathable air in New Delhi and many other places, and really demand to review and have genuine talks about how we can do better.
Sure.
And what else? Similarly, products that require a lot of water. What can we do about that to do it without that much water? There are so many real large-scale chemical processes. We've been one of the centers of mining of rare metals and other things in Missouri here until 1980. I will finish, Vivek. Now, others are doing that mining under even more atrocious conditions than we did it. How is that helping? So that's something for the ISCRE program chairs to think about the future. How can they change that? Not totally, but at least somewhat. I thank you very much to listening to my rambling. In my excuse, my university in these transitions, using COVID as an excuse, has removed all my files temporarily on a computer, so I cannot access them, I cannot copy them, I cannot do anything. So I'm totally here with you as a blind man.
No, Mike, I think you have done your job. You have already made very useful points, and I'm sure. I think when we meet at our ISCRE board meetings, I will surely bring this out and see what can be done. Thank you.
Very good. Thank you.
Uh, thank you, Mike. And we'll of course have opportunity to discuss this at the end after all we finish the round. Our second speaker is Professor Manmohan Sharma. I think he's probably the most well-known chemical engineer from India. He was educated at UDCT and PhD from Cambridge. He was appointed as a full professor of chemical engineering at UDCT at the young age of 27. The UDCT now is called as ICT, Institute of Chemical Technology, Mumbai. And he then, of course, became the director of UDCT later. He has made tremendous contributions to chemical engineering science and technology, as well as chemical engineering education. His pioneering research on mass transfer with chemical reactions, intensification of reactions using microparticles, and multi-phase reactors is not only extensively used and cited, but has also translated into many commercial plants. His contributions are recognized by numerous awards. In 1990, he became the first Indian engineer to be elected as a Fellow of Royal Society, so FRS UK. He was awarded the Padma Bhushan as well as Padma Vibhushan by the President of India. And of course, he has variety of other number of other awards: Livarium Medal of Royal Society, SS Bhatnagar Prize, which is the highest prize in sciences, in engineering sciences in India, FICCI Award, Vishwakarma Medal, Meghnad Saha Medal. He's a fellow of all national academies of India and so on, IChemE and so on. He is the only chemical engineer from India to have an international medal on his name by IChemE UK. There is a Professor M.M. Sharma medal by IChemE UK. He also became an independent editor of Chem in Science at a young age. He has taught and mentored many generations of chemical engineers, including myself and technologists in India. Today, he will be speaking on contributions of CRE by Indian academia and industry. Professor Sharma, please.
Thank you, Vivek. First of all, let me compliment you and your IIT team for this extraordinary program that you have unfolded in spite of all the difficulties. I have myself vivid recollection of ISCRE because in 1988, I gave a plenary lecture in Basel, in Switzerland, when the topic was multi-phase reactions for fine chemicals. Now, I take you back to mid-60s when, as Vivek told you, I became professor. We had rudimentary facilities, no fund for research. Funding was exceptionally poor. So we had to take up idea-centric research. And therefore, I want to say our DNA at that time was that ideas matter a lot and that real problems are far more challenging than fictitious problems. And in applied sciences, it is very important for us to have a lively pipeline link with industry. And to put PhDs, the only way universities can thrive is through PhD research. And PhD research, unless we find a placement in industry. So I had to go to managing directors of several chemical companies in India and the managers to tell them how PhDs will make a difference. And within a matter of 6-7 years, we didn't have enough PhDs to supply. I'm mentioning this because the topic that you want me to talk about, linkage between academia and industry. So I mentioned to you that we were on idea-centric. Now, in gas-liquid reactions, methods of measuring interfacial area, which is very crucial for design of any gas-liquid reactor, is very well-established procedure through, and we also contributed to that. But there was a complete blank on liquid-liquid reactions. Number of people throughout the world were attempting, including in Netherlands. We came up with a very simple idea of formate esters alkaline hydrolysis, which can become a very model system, very simple and very cheap system to measure interfacial area in liquid-liquid system, even gas liquid-liquid system, or even when solid particles are are present, and they are of direct relevance in the design of liquid-liquid reactors. And we made use of this strategy in industry. Then we moved on to another idea-centric research, that was what happens when particles are smaller than diffusion film thickness. You call them microphases. And my colleague Ramachandran, who was my early PhD student, and he did a complete analysis with the background reaction of flue gas desulfurization, that if the lime particles were to be smaller than diffusion film thickness, how much increase in the rate you will get. And it was an extraordinary piece of work, completely theoretical to start with. And no less a person than Professor Sherwood made a mention that he wanted to tackle that problem, but found it was already tackled. And it has direct industrial relevance in other related reactions. And shortly, I will explain to you a specific case of a slurry reactor as well. Continuing this theme of role of microphases, we showed that many reactions which in aqueous, like for example, butenes in sulfuric acid, the solubility is extraordinarily small. But if we could emulsify, say, chlorobenzene, in which we'll have thermodynamic solubility of butene, we'll get marked increase in the rate of absorption of butene. This was theorized and proved by experiments. Now, this has relevance in several contexts in industry, and we have made use of that. And this theme we pursued further, that how heterotrophs can intensify reaction, how micellar catalysis can enhance the reaction rates and all. All of them were at extremely low cost. They are predominantly idea-centric. We took this theme further, and how the diffusion film, what happens in the diffusion film can do wonders. And I give you an outstanding example of chlorine being absorbed in hot caustic soda, and hypochlorous acid is stripped out. Nobody will believe if you tell them that this can be done. But chem in science will tell you that if you can have rate of stripping of HClO higher than the rate at which it goes into the bulk phase, you will succeed. And more than 70% selectivity of chlorine absorption in caustic soda to give you HClO was established by little theory and experiment, and it had a very large implication in the manufacture of epichlorohydrin. And Dow Chemical Company, where I happened to give a seminar, have actually implemented that idea of making epichlorohydrin through this intensification process. So the whole business of what goes around in the immediate vicinity of the gas-liquid or liquid-liquid interface is something which we pursued relentlessly over many years, and newer ideas. I'll share you one more idea, that how hydroiodic acid is manufactured. So H2S is absorbed in iodine, dissolved in iodide. Iodine itself has no solubility in water. Iodine dissolves in sodium or potassium iodide solution, becomes, Ki3, Ki4. And if you absorb H2S in this, you will get sulfur plus hydroiodic acid. If this sulfur is colloidal, smaller than the diffusion film thickness, then the rate of absorption will H2S, because H2S complexes with sulfur, goes up markedly. This was shown by theory as well as by very simple experiments. And my colleague Anurag Mehra did this work. The HClO stripping work was done by G.D. Yadav and Lahiri, and we have seen clear-cut implement. But there's another implementation of what happens when you have a second liquid phase which emulsifies, leading to unwanted products. So when you take propylene, chlorine, water and make chlorohydrin, you get unwanted dichloropropane. If dichloropropane emulsifies and particle size is smaller than diffusion film thickness, chlorine solubility in water is extremely low, but in dichloropropane it is thermodynamic. And you will have more and more production of dichloropropane rather than propene chlorohydrin. And this was demonstrated. One of the industrial units was able to confirm this feature, that whenever they had adventitious emulsification, they got into this kind of a problem. Then we moved on to some other areas. Now, equipment-oriented research for multi-phase reaction was hardly done in India. So you saw presentation of J.V. Joshi, who collaborated with me as my PhD scholar in early 70s, and we were the first one in India to bring out the efficacy of gas-inducing impellers. Till then, there was not a single gas-inducing impeller-based hydrogenator or oxidizer. And it revolutionized. And of course, many people picked up this idea. Large number of hydrogenators are being fabricated in India by companies taking up these ideas of the beauty of this was that you got an impeller which not only gave high values of KLA, and that too at lower power consumption. So as J.B. Joshi explained, many of these hydrogenators which were taking 30 hours collapsed to something like 3-4 hours. And industry people, first, they had kind of diffidence whether it will happen. And when it happened, there was a glow on their face, because the same equipment with lower power consumption was giving them such kind of performance. So same thing in mechanically agitated contactors, that new impellers can make lot of difference in terms of mass transfer behavior at lower power consumption. Now, when I mentioned to you earlier that real problems are far more challenging than fictitious problems, and there is a lot to learn from what goes on in industry. We can get many ideas from industrial operations. The classic Solvay process of 1860s, and it gave us the clue which Ernest Solvay had by intuition done the sectionalized bubble column for the Solvay tower. As you know, Solvay tower was an epoch-making operation in the history of chemical industry. And J.B. Joshi was able to prove that what he did intuitively by doing proper modeling through the circulation model, where Mike Dotkovic has also done a lot of work, we were able to show that kind of separation was close to what Solvay had done. You know, this pursuit went on all the time. Our motto was, academic work first must concentrate on teaching. When we do consulting, it must be in addition. And whatever work we do, like surgeons in a medical college, that they must perform surgery, we must demonstrate our capabilities in the marketplace. After all, final habitat of research is in industry. And to convince the people in industry that you can get more out of the existing equipment is not an easy thing. And you have to have a missionary zeal, and you have to be very accommodative. Never claim that you did it. You should always say, we did it. This is one of the lessons I learned. And another lesson I learned interacting with industry was to tell them that if anything doesn't work, you say, Sharma gave that idea. So they are free from any failures. One of the big problems in Indian culture is we don't have culture to own failures. That is one of our great weakness. And you get rid of this in industry by telling them, whenever some idea doesn't work, it is me who gave that idea, and I tell you, it had a fantastic effect. I'll conclude by telling you something about this role of microphase in a slurry reactor. The live example was oxidation of sodium sulfide Na2S with oxygen, of great industrial importance. And it's catalyzed by activated carbon. We were able to show by theory and experiment that if activated carbon particles were smaller than diffusion film thickness, that means we took activated carbon particles 3 or 4 micron. This is the only paper in Chem in Science in the slurry reactor where you show catalytic effect of smaller size than diffusion film thickness, leading to a dramatic rise in the rate of oxidation. Lastly, I tell you that we did fair amount of work on dissociation extraction to separate acidic and basic aromatic substances which you cannot separate by distillation, by making use of differences in their dissociation constant. And this was also adopted in industry. We published many state-of-the-art papers, many research papers in this area. In essence, I want to emphasize, and I was glad to see Professor Jensen's thing, that chemical engineers better have some hardcore knowledge of chemistry. That is what chemical engineers are distinguished from other engineers. Only branch of engineering which makes use of chemistry. So when you say chemical reaction engineering, please make sure that you understand the chemistry of the reaction. This is one of the messages I like to communicate. I like to confine to the time given to me, and I thank you. And I'm enjoying the presentations being made. Thank you.
Thank you, Professor Sharma, and thank you for reiterating the message which you are giving us all these years at ICT. Thank you so much. We'll move on to the third speaker. Today, we have Professor Andreas Seidel Morgenstern. He is the director of Max Planck Institute for Dynamics of Complex Technical System in Magdeburg and chair of chemical engineering at Otto von Guericke University, Magdeburg, Germany. He received his PhD from Institute of Physical Chemistry, Berlin. Before joining as a professor of chemical process engineering at Magdeburg, he also worked in an industry in Berlin. His research interests include heterogeneous catalysis, adsorption and preparative chromatography, crystallization, and development of new reactor concepts. The results of his work are published in more than 500 research papers. He has received numerous awards, including, for example, Max Buchner Award of DECEMA. He also holds honorary doctorates of the University of Southern Denmark, as well as the Lappeenranta University of Technology from Finland. He is a member of German National Academy of Science and Engineering, and he recently received Affordable Green Chemistry Award of ACS, American Chemical Society, together with Professors Gilmore and Seeberger. Today, he is going to speak on CRE for fine chemicals and pharmaceuticals. Professor Seidel Morgenstern.
Yeah, thank you very much. Is my voice okay? Can you hear me?
Yes, yes, quite fine. Yeah.
So let me say, first of all, that I would have liked to be very much in India and to join you personally. We had, in fact, in 2020, in February, a German Indo workshop, and Pushpa Varnam from IIT Madras, myself, organized it. Shantanu Roy and many of the Indian colleagues visited us, and ISCRE was announced there, and we were preparing to come here. And now we end up in this virtual meeting, which is very unfortunate, but I'm quite sure it will be successful because we need this exchange of ideas. And I would like to thank you very much for taking all the organizational burden of that. So then let me come to the topic of my talk. I will second and complement a bit the lecture Klavs Jensen just has given. And if you allow me, I think I will be more efficient if I can share with you 2 slides that could be maybe speed up my lecture a bit. I will try to share it with you and need to arrange that.
You can even share the whole screen if that is easier. Whatever is easier.
Yeah, I will do the whole screen, and then I hope it will come in a second. So then I hope you can see that already.
Not yet. Oh yeah, it is coming up now. Yes, we can see it now. Go ahead.
Yeah, I have this introductory slide just to bring you the location of pharmaceutical industry, the production of fine chemistry in this tree. I like this figure very much. I use it in my lectures. It shows where we come from, which small number of raw materials are the starting point, and how far we go up in the diversification in this tree. So the chemical engineering knowledge more or less was generated mostly in the lower part of this figure for these large-scale processes. We have so much knowledge and have optimized them over decades partly. In the upper part, there is the situation a little bit different. We have so many diverse products, the specialities, so to say, and these developments there are often driven by the chemistry. That means also by the chemists that developed the chemistry. Very often numerous steps are needed to end up in a final product, let's say a drug. Long development times, too long very often, are needed to develop these processes. Batch is still dominating. And of course, if you look from an engineering perspective, all these processes are very far from being optimal. And of course, there are other constraints coming from the authorities. FDA was mentioned by Klavs. So there are severe regulations very often. So on the second slide, I want to show you a bit my view on that field. My personal experience is related mostly to work with the production of pure enantiomers, so the stereochemistry, so very demanding synthesis reactions have been studied in our group over the years, and more recently also the exploitation of natural products after extraction, transforming some of them. So we had in this area numerous projects with many industrial partners and also with academic colleagues in huge European consortia. So my observations are these 5 points here that I want to share with you. Very obviously, in this area, there are long process chains that lead to the final product. Now, this is difficult to oversee, and as a whole, very often not in an early focus, at least not in the focus of many people involved in these developments. So the process development is further characterized by the fact that there is a rather limited database. In particular, what the chemical reaction engineers like to know a bit about the kinetics of the reactions in a quantitative way. This is very often missing, sometimes totally missing. In this area also is my observation that there is a low level of recycling concepts, or thinking of recycling as a very important ingredient. This is more to see in the bulk chemical area, but in this area the product is expensive, you want to have it, and waste sometimes is not so relevant. This low look on recycling is partly due to the regulations. So sometimes it's not possible to recycle certain ingredients of the process without making sure that they are very clean, and these additional efforts are just not taken. And to reach high purities, which are required often, you need very often to apply in combination to the reactions dedicated separation processes. For example, crystallization and chromatography are very often used. These are very selective processes that can help reaching the required purities. We have our self-experience in the area of processing natural products to get out just a certain target, maybe after transforming this valuable component originating from nature. And what was my final observation that I want to share with you here is that typically in this area, people don't know too much about the large-scale bulk chemical processes or processes that produce the commodities. And knowledge from this field is not sufficiently exploited. So by Klavs mentioned transition from batch to continuous is for chemical engineers not a big step. This is very natural to compare both. We have tools, but in the pharmaceutical industry, they are very often not too much known. So let me come to the lower part of the slide where I try to summarize a few requirements or suggestions what in the future chemical engineers should do much better and much more in this area. And again, I second and complement Klavs' lecture in a way here. First of all, and Professor Sharma just said the same, we need to understand the chemistry well as engineers. To be a partner to the chemists, we should know their language very often much better than we know it so far. The chemists need to accept chemical engineers as good partners, and that needs a minimum, I would say, of joint vocabulary. In this area, there is needs to be something done, I would say. In this area is also a big progress which the engineers know well, which is driven by theoretical chemistry, but engineers apply it in the field of molecular modeling tools. There is huge progress. We are able to predict certain physical properties quite well now from the computer. We can use this for screening. The important issue of solvents in this field can be substantially supported, or the identification of suitable additives. This can be, for example, co-solvents, or maybe partners for forming co-crystals, or of course the big field of catalysts in this area. The chemical engineers are quite good in designing experiments, measuring data, and the machine learning area is also a domain where we are active. So we should really input this into these pharmaceutical developments, as mentioned in the previous plenary talk extensively. So this is probably a field which will flourish in the future. But seeing the rather long process chains, the knowledge about reactions is not enough. We need to understand also better the separation processes in quite some detail, because only jointly they will be used, and we need to make compromises probably in a continuous process on both sides, and that requires a good understanding of the separation side. So the last point, chemical engineers are good in modeling and structuring processes. We could help reducing this complexity, and we could maybe generate reduced models which are needed and valuable for overall process developments. In particular, we should not give up to insist that a good understanding of reaction kinetics is the key of everything in our area. So, and to use machine learning concepts can help here, but in a way, we should not give up a deterministic understanding of the reaction mechanisms as we have been trained. That will be needed and very beneficial. And in the end, all this can help, of course, to shorten the development times that are by far too long for pharmaceuticals. We now see that in the field of the pandemic, how important it is to end up quickly with required medication, and in this case, vaccinations. So I guess these were the two slides I wanted to share with you. Maybe I go back now to return to the main screen, and this was the message I wanted to convey to you. Thank you very much.
Thank you so much. Thank you so much. And will, of course, I have a question or two, but we will talk about the questions later. Let's move on, and we have the fourth speaker, Professor Mike Harold, who is the Cullen Engineering Professor of the William A. Brookshire Department of Chemical and Biomolecular Engineering at the University of Houston. Before joining University of Houston, Mike worked at DuPont on several technical and managerial positions, as well as at University of Massachusetts at Amherst as associate professor. He is the founder and principal investigator of University of Houston's Texas Center for Clean Engines, Emissions, and Fuels, which was established in 2003. In 2000, Mike joined University of Houston as the Dow Chair Professor and the department chair, a position which he held for 2 consecutive 8-year terms. Mike has been editor-in-chief of AICHE since 2012. Over the past 2+ decades spanning academia and industry, Mike has coupled probing experiments with predictive models to elucidate the interactions of reactions and transport processes in catalytic reactors. He has advanced the understanding of multifunctional reactors and their use in energy and environmental applications, including the membrane reactor for coupled hydrogen generation and purification, and the adsorptive reactor for lean NOx reduction. His pioneering research has helped to reduce the byproduct formation, to improve reactor safety, and to intensify overall chemical processes. Areas of particular interest include reaction separation devices and materials, catalytic reaction engineering, and combustion processes. He has received many awards, including the Excellence in Applied Catalysis from the Southwest Catalysis Society in 2019, the Esther Farfel Award at the University of Houston in 2013, which is the highest award bestowed on a faculty there. So with this brief introduction, Mike, floor is yours. Oh, sorry, he is going to speak on CRE for environmental applications. So Mike.
Thank you, Vivek, very much for your introduction. And let me try to share my screen. Okay. I'll be right with you.
Sure.
Okay, hopefully that is visible.
Yes, it is coming up. Yeah, sure.
Okay. Well, thank you, everyone. And it's great to see my friends from afar, and congratulations for organizing this ISCRE Symposium. It's interesting to see Mike Dudakovich there. I got involved in ISCRE board back in the 2010, I believe, Philadelphia meeting. Professor Dudakovich cornered me in the reception area and said, I have an offer that you cannot refuse. And I'm ending my 12-year term in 2022. Thank you, Professor Dudakovich. Well, anyways, the points I want to make in my few minutes is on the environment. I think arguably this is the most important area that we all work in as catalysis and chemical reaction engineers. There are several items here that I think I'd like to elevate in terms of the environment. Certainly decarbonization, we all know the challenge we face. Linked to that is natural gas utilization, natural gas being a bridge fuel, and the importance of exploiting hydrogen content of methane. And of course, air pollution is always an issue, but now that's being elevated because of greenhouse gas emissions, water pollution with microplastics accumulation, and finally renewable energy, which we all want to see, but we know it's going to take some time to get where we want to be. Now, we've all seen plots like this in our various locations about greenhouse gases and the dire outcome if we don't do anything. It's not just CO2, it's methane and N2O and fluorinated gases. The recent developments with the meeting in Scotland are encouraging. Now, decarbonization. As chemical engineers, we contribute a lot to the CO2 emissions, obviously, through no fault of our own, but now we have a challenge to change all that. These are a few reactions that are culprits for very large CO2 footprint. I elevate methane steam reforming, a highly endothermic reaction that produces 10 pounds of CO2 for every pound of product due to the very hot furnaces that are driven by the combustion of various fuels. And then there are others like ethane steam cracking and olefins production, the HCN process. The list is very long, in fact. So that raises the specter of a paradigm shift in catalytic reactor design, really advanced by Guy Morin and his co-workers in a science paper. rather than burn fuels to generate the heat and the temperature to drive the chemistry. I'm hearing an echo.
My slides are not changing. We are still seeing the slide. Yeah, now it is better.
Okay. Not sure why slideshow mode is not working. So yeah, just emphasizing this glowing orange is a problem that we all know that endothermic chemistries have, and that's we're burning fuels to generate the heat. So we need a new way, and one is to electrify catalytic reactors through ohmic heating, advanced by Guy Marin and his co-workers. More recently, Vamiri Balakataya, my colleague at Houston, will have a paper appear on new concepts in electrified catalytic reactors, one of which is shown here, where we apply a voltage over a grid of metallic substrate, which may in fact be coated with the active catalyst. Raises a whole host of questions about how we design these reactors. There's a lot of interesting concepts that can be investigated, and those are depicted schematically over here on the left. There's modularity. If one thinks about natural gas being a distributed fuel, then we can bring the process intensification concept to bear rather than these huge plants that we all know and love. And finally, the whole driving force here is that we want to use wind and solar and maybe nuclear to drive these endothermic processes, which are really the only way we know to do certain chemistries to enjoy the lifestyles that we live. Now, from decarbonization, we have natural gas that is plentiful throughout the world as a transition fuel. Before we get to green hydrogen, there's blue hydrogen. I just show one example here where this was an example advanced by Shell a couple decades ago, where one at the wellhead would take natural gas and reform it with steam to a mixture of CO2 and hydrogen. Using a membrane concept, one can then extract hydrogen and send it into a pipeline and then put the CO2 back into the ground at the site of the well. Now, this is not commercialized, but these are some of the ideas that we as CRE researchers need to really focus on and convince, as Professor Dudakovich said, the politicians to fund the research. Now, air pollution, chemical engineers arguably are both the culprit and also the problem solver of bad air days that we see in Houston, good air days that we all want. I'll give you an example of where chemical engineers and specifically chemical reaction engineers have had a major role, and that's in catalytic emission control. That's not stopping. It started back in the mid-1900s with Houdry and the catalytic converter concept. That was necessarily commercialized after the U.S. Clean Air Act in the 70s and led to many successful new generations of the catalytic converter for cars and then trucks and then ships. In recent years, diesel has been the focus, and that has led to amazing clean diesel engine technology. Now, my colleague Bob McCabe, who's now at NSF, has correctly pointed out that the catalytic converter is probably arguably the most complex catalytic reactor and arguably the most successful demonstration of catalytic reaction engineering, many decades old. And there's many attributes of the catalytic converter that Bob listed in a talk that he gave about 10 years ago. I should mention that the picture behind Bob is actually of the late Haran Gandhi, who was a recipient of the National Medal of Science in the US for his work at Ford, advancing three-way catalytic converters. Now, in diesel, we have a very good example in recent vintage of the positive impact of government regulation and catalytic reaction engineers solving the problem. And this is the solution, a chemical plant on wheels that now is on most modern diesel vehicles that ensure clean emissions from a very dirty combustion process, eliminating multiple products in favor of CO2, water, and nitrogen. And technology continues to advance. Instead of 3 reactors, there's probably going to be 4 or 5 eventually. Now, let me close by saying the problem doesn't stop. In order to achieve sustainability in air and water pollution, we have to keep doing research. And obviously, the dire challenge that we all face in humanity is greenhouse gas warming, and CO2 and methane and nitrous oxide being the culprits. I identify methane being the other greenhouse gas because it is a very large percentage contributor of warming because it's at least 50 or more times more potent than CO2, over 100 times during the first 20 years of its emission. It's rising in the atmosphere, as is CO2, while it's multiple orders of magnitude lower in concentration. The fact that it's 2 orders of magnitude more potent raises the specter of its importance in eliminating it. I'll close by saying that there's been recent research, including in our lab, moving from the 3-way catalytic converter to the 4-way catalytic converter and changing the game in terms of natural gas as a transportation fuel. Our EPA has justifiably called hydrocarbons up until now non-methane hydrocarbons, but now methane is being lumped in as a important pollutant because of greenhouse gas warming. And that's another problem to solve in this list of problems that we must solve if we are to really make inroads economically into solving the global warming problem. With that, I'll stop now and be happy to participate in the discussion. Thank you.
Thank you, Mike. Thank you so much. What I will do is I have few questions, and while I'm waiting for other questions coming up to my desk, let us probably start with the questions which I have already collected. And these are kind of a blend of questions addressed to probably topics with you, but I'll probably start with the relatively simplest one, which all of you can address as a panel. So the one question is like chemical reaction engineering always started as initially data-driven models. In the sense, the basics of it is reaction kinetics. So initially we started with empirical models. So you collect the data, build empirical models, and use them for reactor simulations. Then there was a trend of building more mechanistic models, maybe using DFT or ab initio calculations. But now again, trend is moving to machine learning and again going back to data driven. So it will be useful. So Chetan, this is a question posed by Chetan Gadgil from National Chemical Lab. So it will be useful to understand your comments on the mechanistic based focus versus the machine learning based focus, which eventually people are driving the field at.
I could make an attempt to answer that first. I work with Professor Lars Grabel in our department here at Houston, who's an excellent DFT scientist. And Lars and some others in that community have advanced descriptor-based DFT, and that's an excellent shortcut way to apply DFT to identify catalysts that have certain properties that either accelerate select rate or increase selectivity. We've used that approach with Lars very successfully on a number of applications, including methane oxidation. And it helps not only in defining pathways, but also in providing kinetic parameters for microkinetic models that are critical for complex chemistry. So I'm a great believer in DFT and it in terms of helping accelerate the reaction engineering side of the equation.
Anyone else want to add on? Yes,
Maybe.
please, Andreas. Yeah.
Maybe I can also address this kinetic problem a bit in this field of pharmaceuticals, where there are many complicated molecules, a lot of similar molecules, enantiomers, isomers. I think the challenge is very high to get a very detailed understanding of it. What counts here, from my point of view, is to have a decent understanding of selectivity problems that come up if you process this, to which ratio you lose valuable feedstock into an undesired direction. And there are relatively simple models, a very good start. They are even missing in this field. If you start here too ambitious, then you come not to an end in the time you want to see results. Both is needed. I think these simple network models, which give you an idea of the selectivity, should not be underestimated in their potential. Of course, everything depends on the quality of the data. How much can we measure? Can we measure the side products? Do we have an understanding about them? Very often they are not available as standards. You have sometimes to produce some models for calibrating measuring devices. This is a long way. So to validate very detailed models is maybe a second step from my point of view.
Sure. Thank you. In fact, that brings me to the other question when you talked about validation. So everyone is talking about multi-scale modeling, and Mike Dudukovic has also mentioned that from several, and there are several talks in this ISCRE program. So there is a question which is asking that every model will have some uncertainty associated with it. So if you are essentially building, say, 4 layers of scale, so if you are tackling and developing and linking models are developed at 4 scales and then building the overall model, how will you anticipate and estimate the uncertainty associated with the overall predictions of that multi-scale model? Because every scale model parameters will have some uncertainty, and which will build on as you build the multi-scale model. So probably Mike or whoever. That's the question.
Yeah, typically you have a part of the whole problem that you understand better. You have maybe quite realistic results. And there are very often in such long process chains, Klavs has shown examples. Some pieces are not understood. Maybe the separation is very crude. Then one should be really very careful to pretend to be in the position to have a reliable prediction of an overall outcome. There will be mathematical tools around, but the weakest point in this chain will decide then about the quality. And so to synchronize this a little bit, to invest in the weaker points more than maybe in the points that we understand already very well, because we like them, we have studied them over the years. To identify these difficult parts in the process chain. This is a bit also a field of experience of more senior people, I would say. So for younger people, they might quickly don't find this step easily.
Professor Dudukovic, yeah.
Well, you are not going to build multi-scale models in order to later interpret the large-scale one necessarily. That's not the meaning of it. You are trying to get the right level experiments to answer what are the key time constants, the key species that play a role at different scales. And a combination of experiment and model then is needed on every scale to some extent. It's simple, just a simple model will answer your question. You can test it, you can get the quantity, the picture, and move up. And that reminds me that Mike Harold is right when he said that one of the greatest successes in our profession were the catalytic converter for cars. And part of their success in the 70s, early 70s, was the mandate, the government mandate, thou shalt not emit more than this from the end of the pipe, period. Otherwise, we could have taken another century to debate, but which fine point in this catalyst formulation or in this model could play a role and so forth. So having firm goals. So I would change your question around what should we do? What would be the critical experiment to prove that the doomsayers with the CO2 scenario are right or wrong? Because, there is too much bad blood, too much confusion generated from these things. Well, if you let it rise above 500 ppm, the earth is doomed. There is no evidence for that. Absolutely none. Of course, that's one way of interpreting what you see, the data and so forth. So, Einstein, I think, said, well, I could do million experiments to prove that I'm right. Still, nobody will believe me. But I can think of one. If you can think of one that can prove immediately that I'm wrong, I would like to see it and I'll believe it. So that's the problem. We don't need the machine learning is just still the means of saving money, eliminating people's thinking, and telling machines use what we once talked about and now know how to computerize. There is no creativity in that. Nothing other than speed of producing more answers. If you program the chemistry right, you will get the right answers. If you program it wrong, you will get all sorts of fabulous answers that have no basis in fact.
Sure. Thank you. So I think the next question is for Mike Harold. It is by Professor Enrico Tronconi. I'll just quoting his thing. So thank you, Mike, for mentioning electrification of chemical processes as one of the next CRE challenges. What are the main hurdles in this area, in your opinion?
Hello, Enrico. Look forward to seeing you again in person. Well, like all of you. There's really two, I think. One is scale. During this session, I went to the kitchen and I toasted a bagel, and I have an electrified unit that did that, and that was ohmic heating. So now we're thinking about using that to do methane steam reforming. So how do we do that on the world scale? Does it have to be done in modular units and then scaled out? That makes me a little bit nervous because of the economy of scale issue. So there's the scale issue and how large can we make it? And secondly would be more the catalysis. As Guy Marin showed in his science paper with Van Giem, putting the catalyst on the metal substrate directly certainly is appealing. It's not unlike a monolith reactor where you have a thin film of catalyst, but is the heating of the substrate going to cause deterioration of the catalyst? So it raises issues of material compatibility and whether you'll get delamination. Can you have a robust thin film to pull that off to take advantage of the high surface to volume ratio that you can hopefully achieve?
Okay, thank you. So there's one more question again on CO2. But that probably can be answered by a general panel. So that question is like, there are essentially three ways for reducing CO2. So reduction in CO2 emission, utilization of CO2, and sequestration of CO2. So which are, in your opinion, which path is more preferred, and where CRE will have largest impact? That's the question.
Can I tackle that?
Please.
If I may, first. I'm sick and tired of this business of CO2 sequestration, digging holes in the ground, pumping it in there, and so forth, and hoping that our researchers in geology can address the question in which form it will be 2 centuries from now. CO2 is an important gas. We have plenty of uses for it. Find the chemistry, especially if the doomsday comes and methane starts getting released for the permafrost, which forever, which I don't believe, but let's say it does, then what are the chemistries that can combine methane and CO2 in something that we can use? Utilize the CO2.
Okay.
That's the only common sense answer.
Sure.
Or
Thank
recycle
you.
it, which is saying the same thing, but not recycle playing the game out playing forests, where the trees, the rate is of order 1, the combustion is of order 10,000. So how will you match the rates? I mean, they all, there is, what I'm afraid that our whole literature is getting flooded with nonsense, and the people in finances, they love it because they can trade then CO2 credits and things like that. And so select the panels that will put up ideas how we can use waste CO2 and combine it with something else that we have plenty of, but it's unwanted. And don't worry where the energy will come from. Ultimately, will have to come from the sun. And we cannot develop everything and answer every question, immediately.
Anyone else want to comment? Or okay, Professor Sharma. Yeah.
One is bring down the energy consumption in CO2 removal. So, the main processes are back in vogue for trying to find out better means, better strategies of reducing energy consumption in desorption. That is one part. So CO2 recovery is still going to be continued with absorption with reaction for lean gases. For rich gases, you can use adsorptive separation. So first question is to get CO2 itself. The other part is try reforming of methane as the highest potential of using multi-million tons of carbon dioxide. But the emission from thermal power station is in billions of tons. So the decarbonization is not going to be an easy job in foreseeable future, notwithstanding a lot of gibbering that is going on, I wanted to just pose one question, if you permit me. It's a very interesting and critical problem in reaction engineering, what I call the syndrome of PPM engineering and PPB engineering. The person, our colleague who is working in pharmaceutical, a big problem they are facing is impurity. We're not talking of purity anymore. We are only talking of impurity level in some cases like dimethyl nitroxide at PPB level, 5 ppb, 10 ppb. Now, how is reaction engineering going to train itself to look at problems where you are dealing with not the purity of the product, but the impurity profile, PPM engine? There's only one chemical where the word purified precedes, purified terephthalic acid. There's no other. But in pharma, I have myself encountered problems, and it becomes a forensic analysis that how that impurity has crept in. Maybe Professor Andreas can make some comment on this.
Sure. Thank you, Professor. Andreas, you want to add something?
If I come to this question directly, this is, of course, very, very important, very relevant. And chemical reaction engineers alone will have a hard life to solve this. We need really the knowledge on the separation concepts. And in this area of very high purity, crystallization is a strong tool. We need to exploit this extensively, and we need to understand the solid-liquid equilibria, and maybe understanding even things like polymorphism, different solid states are possible. I think joining forces, separation people and reaction engineers. Otherwise, this will fail.
But sometimes the forensic analysis of what reactions could have conceivably led to the formation of that impurity which is carcinogenic. It is something I myself involved in a couple of forensic analysis of how these impurities crept in. And reaction engineering and separation, as you rightly pointed out, go together. But even after smart crystallization, you are not able to bring down that impurity. And many of the units in the world were shut.
Then you need then dedicated crystallization processes. There are sometimes a solid solution. So in the solid phase, you have impurities as a solution, and the multi-stage crystallization can then help. But this is specific technology. But
maybe Mike Harold wants to comment, and then I go to the one last question. Yeah, Mike Harold. Yeah.
If I could add on the CO2 issue, I encourage everybody to read a perspective paper in AICHE Journal by Scott Stevenson from SABIC, who did an analysis using the first law of thermodynamics, showing that it's fruitless to try and convert CO2 to anything, because unless there's a government mandate, like Mike Dudakovich mentioned, it makes absolutely no sense to take CO2 and convert it into anything. That's one point I want to make. The second point is we have to solve the low-hanging fruit problem, and that is to stop generating CO2 through things like electrification, if we have large-scale wind and solar. And then finally, really pushing back a little bit against Mike Dudakovich, which is always a dangerous thing to do, but Exxon has announced a consortia of 11 companies that will basically convert the greater Houston area into a CO2 neutral region using CO2 sequestration. So, and it's not going to be inexpensive.
Right. No, so I think, Mike, please allow me to temporarily halt this discussion, because this will extend, I know, quite a lot. Probably time is running out. Maybe one question I want to take up, and then probably we can discuss that offline. I think I want to combine 2 or 3 points in one question. All of this is related to education, chemical engineering, future of CRE education. So one point, someone is asking that usually CRE deals with concentration, yield, selectivities. Most of the earlier products typically can be characterized by concentration or impurity profile, etc. But many new products which are like structured materials, they have many other facets beyond concentration and purity. Right? The shape, aspect ratios, and many other decorations of those MOFs and so on and so forth. So whether our existing CRE framework can tackle these, or do we really need to expand? When there are already multi-dimensional population balances, etc. But the question of the one of the participants is whether our existing CRE framework can be extended to model these complex systems. Another related question is by Shantanu, who is talking about whether it is worthwhile and feasible to create a repository of past knowledge, not just books, but really the case studies, models, data, validation data, and so on. And how do we raise the funding to create that kind of repository? And all of these essentially are related to future of CRE education. So maybe collectively you can probably comment on that. And this is our last question for the session. We can then close our session after that. So anyone who wants to start first? So someone needs to, Professor Sharma, you would like to say something?
See, Please let us not forget that entry of chemical reaction engineering as a course is very late in the history of chemical engineering education.
Right.
And you will find in many early, the discussion on multi-phase reactions was limited. Most of them were solid catalyzed vapor phase reaction and concentrated on that. So there are so many facets of reaction engineering. How much can you compress in a course at undergraduate or postgrad? We have to finally confine ourselves to limited number of things. Idea is to expound concepts. How to tackle, for example, how to tackle solid-solid reaction. That is also reaction engineering. But now we cannot take the entire range, even if you take 60 lectures. How many topics can you cover in that?
Sure.
It's one thing to say that I must discuss this, I must discuss this, I must have this, I must also have the catalytic converter in the automobile exhaust and all that kind of thing, you know.
Right. No, and new machine learning and the several new things are coming up. And how do we cover that in a year? That's the real question.
Many fanciful things come. There was a view, for example, in pharmaceutical, that you will be able to come out with new drugs by predictive method. How much has been the success? Professor Andreas can answer that. They have gone back to ethnopharmacology.
Anyone else? Yeah.
It's challenging for some time. Of course, many things are extremely useful. DFT calculations are very, but you will often find that experiments were done and then they say DFT calculations supported it. Not other way around.
No, sure.
That you first predict by DFT calculation and then say it was endorsed by experiment.
Yes.
Andreas?
So I later learned more about crystallization. In fact, I came quite late to this subject, and now I realize how good it is to have some knowledge about population balances that you mentioned, Vivek, property distributions. So Ramke's book and what is around in this area, we need this in the polymerization, the chain length distribution. Now lignin is a big field to use renewable resources, so that we have a distribution of properties. I think this must be part of our curriculum. People should have some contact with that problem in some courses. I don't know if you have a good colleague that teaches crystallization, that's done. But if there is nobody around, you should do it. That's my feeling.
You know, I have dramatized this in the sense that you put up a plant, make all the investment, chemically the product is right, but it fails and the plant is shut because particle size distribution was not right, loss on drawing was not right. I have encountered such problems. Then to solve that problem on existing plant becomes an exceptionally challenging problem.
Sure.
You must have encountered something like that.
Yeah, sure.
Yeah, if I could add, I'm just finishing teaching 80 young minds chemical reaction engineering at the senior level here at Houston, and it's always an eye-opening experience, and the challenge never goes away on how you motivate young minds to be interested in the field. And we need new talent in CRE, and it starts with motivating the youth. And I think if there's one silver lining to this global problem that we face, is that technology is going to find a way, and we can really motivate the young people to say they can be part of the solution as long as they can solve differential equations, understand chemistry, and so on. So it's been fun.
Well, good luck with this, because you are fighting the lack of proper background by now in those graduates, as you well know, and we always hide from that truth. They just don't have the background. How can you preach good new things, visions, concepts, when people there don't have the background because they all want to just politic around and tell you?
I think
it's just sad. So anyway, Come, I will not leave you get away with the CO2 nonsense, Mike, because the reason why the 11 companies came up with all this wonderful plan, because all they use the current norms how you value something. And if you assign that the value of energy coming from the sun is free to you, and construct to use it into converting CO2, then you gotten rid of your problem. If you put that monkey on your back, the thermodynamically that's totally unacceptable, and you pay the price to overcome that barrier, then of course it's total nonsense. Why even think about it? But if you want to think of two things for the government financing, it wouldn't be that. This would be the private sector answer. We are taking the initiative. We will make Houston clean. Good luck.
Yeah, no, but I think that's okay. I think let's leave aside the CO2, but I will take it as Mike's positive aspect of Mike's comment is, even if assuming that students have not enough background, if we can really generate interest in them about CRE, maybe because of these problems, I think once students are interested, now there are several resources available to acquire that background knowledge, and probably we can probably close on this positive note. Thank you so much to all of you, and also for the audience for raising interesting questions. So thank you again, and I close now and conclude this session, and I give control back to Vivek Buwa, Professor Vivek Buwa from IIT Delhi. He has to make some other announcements and probably provide some information. Vivek, back to you. Thank you so much. Yeah.
Thank you, Professor Ranade, and thank you to all the speakers. Before you all leave, I have some important announcements for tomorrow. There are some instructions about the platform, and for tomorrow's plenary and oral speakers, it is important to understand this. So I'll just enter the platform and show it to you from there. Share them. Share them. Gap with it. Please take the gap with it. This is sharing this. Yeah, it is showing on the back. You put the gap back. So we are live. So that is how you will end here in the lobby, and there is a virtual tour available wherein once you start getting into it, let's go, it will show you, it will give you a virtual tour, but in the interest of time I will skip it. You are already here in the plenary session. For oral sessions you will have to go here, and whichever track that you are interested in, you can go in. Important information is that you can switch in from one room to other room in a seamless way. You go in any of these track rooms, and then you are in a meeting mode. An important feature is that you can it will ask for the permissions for mic and video. I have given it already, so it is not asking. And then you are in a webinar mode. All the speakers, I repeat, all the keynote speakers as well as the oral speakers will be there in this meeting room, and it is like any other meeting room, powered fully with several features. And for the Q&A, I suggest that you can start your video and your camera and mic and interact live with the speakers. All the presentations will happen live, so that the presenters can come in this meeting room, share their screen and deliver their presentations. The participants can ask the Q&A live, and then you can again go back to lobby. You can go on to different oral tracks. The sponsors information here is there here in the exhibitor room, and then you have an information center here that will provide you the information on sponsors, the program, etc., and all other resource material. You can also go to the networking center, and then you have a possibility of chatting or talking to the other participants live. Please remember this. You can also make video calls or audio calls to the other participants from here. And by using this bottom bar, you can again come back to whichever room that you want in a seamless way. You can click on this help desk, and then you will have the chat support. You have agenda here, you have chat support here. And interestingly, for poster sessions, you enter here from the link or from the bottom icon here. And if you go for 6th of December, which is tomorrow, you see the posters organized in different categories, in different tabs. The posters are listed with their title, with their authors, and you can look at the PDFs. There are at some locations, wherever the presenters have provided us with the video, we have uploaded the corresponding videos, short 3-minute videos. All the posters are available in the respective rooms. What is more important is that you can also interact with the poster presenters live. And for this purpose, we have earmarked 2 slots for the poster presenters to be available in their meeting rooms, and that is from 4:30 to 5:30 Indian time, and again in the late evening from 10 p.m. to 11 p.m. So I request all the poster presenters scheduled for tomorrow to be present in one, ideally in both of the time slots if your time zones permit it, but at least try to be present in one of these slots. And then the participants would be interested in talking to you live. We also have the Best Poster Awards, and the committee members might also visit, would like to talk to you in this. So to interact in a live way with the poster presenters, you can click talk to the poster presenters, and then all the poster presenters are listed here. You can just press this button connect, and it will take you to the meeting room of the poster presenter, and then you can switch on your camera, you can switch on your audio, and talk to the poster presenters, discuss it. You have a facility of whiteboard, you can draw, you can interact in this. For the poster presenters who are scheduled to present their posters tomorrow, we have already emailed it to you, the individual meeting IDs. Please use the meeting ID marked against your name to be present in those slots from 4:30 p.m. to 5:30 p.m. and again from 10 p.m. to 11 p.m. tomorrow. And make use of this utility or facility to talk to each other. I have some additional instructions for all the plenary speakers and the corresponding session chairs of the plenary talks. You need to join on the links which are sent separately to you. These are the studio links or the StreamYard links. They are different than the virtual platform. I repeat, all the plenary speakers and the corresponding session chairs need to come on different meeting links that we have sent it to you. There is a link that is provided for the test run, which we call it to be a dry run link. Please join that link 30 minutes before the scheduled start of your session. Once we test the settings, you can leave the dry run meeting link and join live on the meeting link. This is only for the plenary speakers and the corresponding session chairs. All the participants, oral presenters, poster presenters will join normally using the virtual platforms. I have already given the instructions for the poster presenters. So we have the tools like chat, video talks in the networking room. Please use it. If you have any problems, put a chat, contact the help desk through chat. If you have any difficulties in joining the virtual platform, we have a helpline email address and a WhatsApp number given on the ISCRE website. Please drop a WhatsApp message and we'll get back to you immediately. That is all with respect to the virtual platform. Jatin, the screen can be unshared. Now we are at the end of the session. Before I close, I wanted to thank all the speakers that we had for today's inaugural session. Professor J.B. Joshi, Professor Jensen, Professor Mike Dudokovich, Professor M.M. Sharma, Professor Cedal Morgenstern, Professor Mike Herold. Thank you very much to all of you for energetic discussions and nice plenary lectures. I also thank you, all of you who are there in the auditorium and who are there on the YouTube. Thank you very much and see you tomorrow.
Yeah, so I think there are a few questions on the chat box. I'll just answer them. Professor Bala is asking, are keynotes in the oral or plenary rooms? Keynotes are in the oral rooms. Only the plenaries, today's session was in the plenary room. The plenary lectures are in the plenary room. And the industry session on the last day is going to be the plenary room. All other talks, keynotes and regular oral talks included will be in the different track rooms, the track 1, track 2, track 3 and track 4. As per, so if you look at the conference program, the program is also arranged according to tracks. So it's kind of intuitive. You can just move on.
Right. Except the plenary speakers, all the keynote speakers and oral presenters, they go to the oral tracks directly on the virtual platform.
Are there any questions? We are waiting. If there are any other questions, we can answer. The book of abstracts and the program, the final program of the conference are also available on the virtual platform. So if you move in, you can see it. Of course, the schedule that you see on the top right, the agenda, that is the agenda button that you see on the top right of the virtual platform also gives you, it's arranged, oral presentation wise. So it is kind of very intuitive to move into those. But aside from that, the PDF document is also available in the information center. So if you search there, then you find the information center, and you'll be able to see the under documents, you'll be able to see the final ISCRE book of abstracts and also the final ISCRE conference program. So you can decide which talk you would like to listen to and so on, and move to the corresponding track room. So I think that is an you can also obviously communicate with us on email, and we'll answer. The WhatsApp number that is also on the ISCRE website. You can message us or call us on that, and email is also a flexible way. So tomorrow we will be meeting again at 1 o'clock.
Yes, 1 p.m. IST. And just a small note once again, you can jump from one oral track to other oral track in a seamless way. Just come out, enter the other room. You don't have to log in or log out. Just moving from one room to other room.
once you've registered and entered the virtual platform, the movement is seamless. You can navigate from anywhere to anywhere.
So that's it, right? So with that, I think thank you very much to all of you once again, and we close the program for today. Thank you.
Thank you. Well, good night here, but it's have a good day in the Western Hemisphere, and I guess the Eastern Hemisphere is already trying to get to bed now. It's near bedtime. So good night and good day to everyone else. Yeah. Bye.